wide open. So if there's any sources off to the side that are shining into the telescope, we will see them. So while Webb is bigger than Hubble, it's not a replacement. Early on, we heard people talking about, oh, there's a replacement for Hubble. Well, not really. Webb is designed to complement and extend with what both Hubble and Spitzer have been able to do. And the key feature of Webb, in order to do that, is it has to work at infrared wavelengths. So I'm going to explain a little bit about what the infrared is, why it's important, why it's really neat, why I do it. If we shine, I should have waited. If we shine a white light through a prism, we get the rainbow thing. We've all seen that. You've seen rainbows in the sky. It's the same principle. It's very natural to ask, well, what's over here? What's past the violet? We also might ask, well, what's over here? What's below the red? William Herschel in 1800 did an experiment where he was trying to measure the temperature of the colors of light. He thought that maybe individual colors might have a different temperature. It was a good experiment to try to do. So what he did is he put a thermometer over here and another thermometer over here as his controls, and then moved the thermometer through the different colors of light. Well, what he noticed was that the purple light was coldest and the red light was warmest. So he did what a good scientist would do and said, well, gee, if it's warmest here, what if I move off just to the side a little bit? I should see the temperature drop, right? Well, it turned out that dark space below the red was the warmest of all, and that's the discovery of infrared radiation or infrared light. And that was the first time we actually discovered energy, light energy that we couldn't see with our eyes. So it was a huge thing, and it took a long time to develop instruments that would work in the infrared, but it came along eventually. What can we do with infrared light? Well, we can take pictures of meerkats. I'm not sure where this visible wavelength picture was taken, but this is what meerkats look like in the thermal infrared, and I think this is a lot of fun. You can actually learn a lot about meerkats based on an infrared image of the meerkats, because you notice the eyes are bright. Your eyes are deep in your head. They're surrounded by very warm tissue, and so they're going to be warmer than average. Their noses, on the other hand, are dark. Your nose sticks out a little bit, and so it cools off a little bit more, and then there's not as much blood supply in your nose, so it actually looks a little bit cooler. Actually, if you go over to the von Karman Museum just next door, there's a thermal infrared camera there, and you can see what your own face looks like, and it won't look like a meerkat, but it will have some of the same features. You also notice that their toes are cold because they're on the rocks that don't generate heat on their own, and so maybe we don't learn a lot about meerkats in the infrared, but we see some of the things. And the gaps in fur are brighter because you can see down closer to their skin, and so that's why their fur looks so funny. Well, there are more important uses for infrared, and one of them is firefighting. If you're in a room full of smoke, it's hard to see anything. But infrared wavelengths, or smoke, is actually relatively transparent to infrared wavelengths. So if we look at this scene with an infrared camera, we see there's a person on the floor that needs to be rescued. And so same sort of thing. He's got a bright face because there's a lot of blood in your face. The clothing is a little bit cooler. I thought it was cool, the oxygen tank on the back of the firefighter is relatively cold compared to everything else, and so it's very dark. So this demonstrates a couple of things that we can take advantage of in the infrared. We can see the temperatures of things. We can see warm and cold, and we can also see through smoke. Well, we can use those same things in astronomy to help us understand the universe around us. This is a little cloud of gas and dust that's zipping around in our own galaxy. It's fairly close to us. All the stars you see here are farther away than the cloud, so there should just be a carpet of stars all over this. But because the dust in the cloud absorbs visible wavelength light the same way that smoke absorbs light, we can't see through the cloud. But if we get an infrared camera and take another image of that cloud, we can see those stars through it. So it turns out there's not much going on in this cloud. It's just kind of quiet, sitting there, not doing much of anything. This is a visible wavelength image of a patch of sky in the constellation Cassiopeia. We see a couple of cool things in here. There's a star that must be emitting a lot of ultraviolet light, and it's causing some gas around it to glow. That's why it has that red color. But in the rest of the frame, you see there's some dark streaks along the edges over here. And it's not because there are not stars there. The stars aren't missing. There's stuff in front of the stars blocking the light. So if we take an infrared image of the same area, we see a number of things popping up. First of all, there's a lot of dust that's glowing brightly in here. But all these very red stars suddenly pop into our field of view. Well, stars form in clouds of gas and dust. So these clouds, there's enough material there that gravity pulls that dust together and heats up and begins to form stars. And so these are the stars that I were talking about. These are the things that are, kind of 10,000 years old, sort of the baby stars. And we can't see them any other way than in the infrared because the dust absorbs them. And so with our infrared cameras, if we want to study how stars form, this is how we do it. We go into the infrared. You'll notice this little box over here that still has the visible wavelength image. If I put the infrared part in there, you see this big ring of gas and dust. There was a supernova there in 1572, Tycho's supernova, that blew out this shell of material, but the material is actually still very cold. So the only way we see it is at infrared wavelengths where we detect the heat from it. Now it's much colder than room temperature, but it's warm enough that we can see it. So in this image, we demonstrated those two features of the infrared that we like. We can see through dust, and we can also see very cold objects. So there's one more scientific technique I need to talk a little bit about, and that's spectroscopy, taking the spectrum of a source. So if you remember when we shone white light through the prism, we got that colored rainbow, so we got all the colors from the white light. If I take a tube of hydrogen gas and pass an electric current through it, it turns the hydrogen into a plasma and it glows this kind of pinkish purplish color. Well, if I look at that tube through a prism, what I'll see is multiple images of the tube, but I only see very discrete colors. I don't see a full rainbow. Well, it turns out all atoms have this have a signature, a thumbprint. And so if I measure the wavelength of those lines, I always see these lines at these wavelengths. So if I look at something and I see a wavelength of 656 nanometers, I know right away that that came from hydrogen. The neat thing is, if I have hot gas, hot hydrogen, it glows at those specific colors. If I have a cold container of hydrogen and put it in front of a white light source, I see absorption, I see dark lines at exactly those same wavelengths. So whether I have hot hydrogen glowing on its own or whether I have cold hydrogen that's absorbing background starlight, I know there's hydrogen there. I mentioned every element has its own fingerprint. So hydrogen is a very simple atom, one proton, one electron, and so it has a very simple set of lines that it emits. Helium has 2 protons, 2 neutrons, 2 electrons. It's a bit more complex. As we get heavier and heavier, we get more lines and more complexity, but they are all a very unique fingerprint. So if I look at a star and I take its spectrum, I can figure out what's there just by looking for all these fingerprints. And in fact, if I take a spectrum of the sun, this is what it looks like. Normally if you you shouldn't look at the sun, but if you do look at the sun, it's kind of whitish, yellowish. You don't see anything particularly funny. But if you look at it through a high resolution spectrograph, this is what you see. And there's a big notch over in the red wavelengths. I said, aha, hydrogen has an absorption line at red wavelengths, so I know the sun has hydrogen in it. And in fact, people that do this for a living say there are 69 elements that we've discovered in sunlight. Hydrogen accounts for 92.1% of the atoms in the sun, helium for 7.8%, and everything else, those other 67 elements, form less than 0.1% of the sun's surface. But we know it's there, mostly hydrogen, a little bit of helium, and that's a common refrain whenever we look at stars. Another thing that spectra tell us is they can tell us how fast an object is moving. You've all heard a siren coming toward you. The pitch of the siren sounds higher than when it's stationary right next to you, and if it goes whizzing past you, the pitch is lower. It's the Doppler shift. Well, light does exactly the same thing. And so if I have my laboratory spectrum, sitting right in front of me, and I compare it to the spectrum of a star, the lines are pretty much the same place. This drawing exaggerates it a little bit, but in general, stars are at rest compared with us in the grand scheme of things, and so the wavelengths are all the same. But for galaxies that are nearby and then some that are not so nearby, they're all receding from us because the universe is expanding. And so the wavelength of those lines shifts toward the red. And so we call this the redshift. So this galaxy actually isn't that far away. We'd say that that had a redshift of about 1/3, 0.3. That galaxy I showed you at the very beginning, that fuzzy little blob, has a redshift of 11, which means that the wavelength of light has been shifted a factor of 12 from what it would be in the laboratory. So that means that visible light from that galaxy has now been shifted way into the mid-infrared, just where my MIRI instrument works. And so if we want to see galaxies near the fringe of the universe, we have to look in the infrared to see the light that we're used to seeing in nearby galaxies. Okay, just a quick side note, as pretty as the rainbows are, they really aren't very useful in terms of analyzing things. So we plot the brightness of the spectrum as a function of wavelength, so you always see plots. And so where there's a bright line, that's a spike on this spectrum, and if there were a spike downward, that would tell you there's an absorption line there. That's important because when we work in the infrared, we don't get rainbows because our eyes don't see that. This is a very young star. This is one of these baby stars that I'm interested in. And baby stars tend to be very messy, just like human babies. They tend to burp up bubbles of stuff and throw things around. But we'd like to get a spectrum of this thing just to understand what kind of material is there. If we do, this is an infrared spectrum. I should have said that at visible wavelengths, we see mostly atoms. At infrared wavelengths, we see mostly molecules. They're larger, they tend to have lower energy states that we're looking at. So this is a spectrum of that baby star. There's a big absorption feature here that's labeled silicates. Silicates are a type of rock. If you go down to Santa Monica Beach, you're surrounded by silicates. Sand grains are a form of silicates. There are also things like water ice, a little bit of carbon dioxide ice, and there's even a little bit of methane gas here. Now, being a good scientist, I employ my prodigious powers of scientific reasoning and come to the very firm conclusion that there are cows in space. Okay, this is a joke. I don't want this to show up in the tabloids tomorrow. A top NASA scientist did not announce the discovery of cows in space. But it's important because these are the molecules that are important for life on Earth. And so it's good, maybe reassuring, that the molecules that we depend on here are actually relatively common in space. And so it helps us understand how our solar system formed, when stars form, they form out of the same stuff that we find on Earth that drives life here. Another thing that we can learn from infrared light is, as we start studying planets around nearby stars, we'd like to study their atmospheres and whether they're rocky or whether they're like Earth or whether they're gaseous like Jupiter. So if we know that we've got a star and a planet, with the planet orbiting the star, we can't separate them. So we can't take an image, usually we can't take an image of here's the star, here's the planet. Generally, we only see the light from both of them together. But if we know that a planet crosses in front of a star transit, maybe you've heard about the Venus transit a couple of years back where Venus passed in front of the face of the sun. When a planet passes in front of the star, it blocks some of the light, and so the apparent intensity of the star drops a little bit. But then there's a phase where we see both of them together before the planet hides behind the star at the other end. But this part is interesting because if there's a big difference in temperature of the planet between the daytime side of the planet and the nighttime side of the planet, we'll actually see a little bit more infrared or a little bit less infrared depending on where the planet is in its orbit. So if we're seeing the backside nighttime side of the planet, there's a little less light. As it swings around to the day side, from our view, it's actually a little brighter. So the fact that the light from the planet and star rose a little bit as we went to to the daytime side, tells us that there's a pretty good temperature difference between the day side and the night side of this planet. And so it probably doesn't have a really thick atmosphere like Venus. It's something a little bit more transparent, maybe like ours. So that's exciting. Hey, we found out a little bit about this other planet. We've been able to do a little bit with atmospheres of planets. This is a model spectrum of an atmosphere. And this is what the Spitzer Space Telescope was able to observe. It was only able to look at this in 3 different colors. And they noticed that it was a little bit dimmer at 3.8 microns than they thought it should be, and a little bit brighter out here at 6 microns. And so they fit that atmospheric model and said, yeah, this might be able to work. One of the things that the Webb telescope will do, it will actually let us get this spectrum. And so maybe we'll actually see that curve and confirm that the atmosphere really worked that way. So if the infrared is so neat, and I hope I convinced you that it is, it's really a lot of fun to play with. Why doesn't everybody in the world and their dog have an infrared telescope in their backyard? Well, there are 3 things that make this a difficult place to have your career. First is room temperature emission, and I'll explain what I mean. Second thing is the atmosphere, and I'll explain what that means. And then third, just the sensors that we use for infrared astronomy can cause a fair amount of trouble on their own. Any object that's at a finite temperature emits radiation with a very characteristic spectrum, and we call this a black body spectrum. Stars that are extremely hot, 10,000 to 100,000 degrees, actually emit most of their light in ultraviolet wavelengths. More normal stars like the sun emit most of their light at visible wavelengths, which makes sense because that's what our eyes see, and so it makes sense for our eyes to have adapted to what our star puts out. So that's why we have visible wavelengths, and that's where the sun emits. Those clouds of gas and dust that I mentioned where we form stars, they tend to be very cold, 15 to 30 degrees above absolute zero. So they actually emit most of their light, their radiation at the very long far infrared wavelengths. And then the cosmic microwave background, which is a little bit under 3 degrees above absolute zero, emits in the millimeter. That leaves this nice curve in the middle. That red curve is in the mid-infrared. Its wavelengths around 10 microns, exactly where my instrument works. And that's where the Earth emits, and where the atmosphere emits, and where astronomers emit. Everything in the mid-infrared is glowing. One of the infrared astronomers quoted, "Observing in the infrared is like observing in broad daylight with a telescope made out of light bulbs." Where do the stars go during the day? They're still there, right? Stars don't move compared to us very much. So they're still there, but we can't see them because the Earth's atmosphere scatters blue light from the sun, and the glow of that scattered light just washes out our ability to see stars. If you got a telescope out in the middle of the day, you actually could see a few stars, but it's really hard because the sky is so bright. Well, that's what it is like all the time in the mid-infrared. So when I said I built instruments that went on Keck and on Palomar, we were fighting the atmospheric glow. It didn't matter if we were observing daytime or nighttime, it's always bad. So that's one reason why we want to put things in space. Second is our Earth's atmosphere isn't very cooperative. That same atmosphere that makes it possible for us to be alive also likes to make it difficult for infrared astronomers. At visible wavelengths in this range, most of the light gets through the atmosphere down to the ground, and so that's why big telescopes on the ground work. But there are certain wavelengths where molecules in our atmosphere absorb all the light, and so the atmosphere is actually opaque at those wavelengths. A lot of it's just from water vapor, some of it's carbon dioxide. There's even a little bit of absorption from ozone in our atmosphere. Well, the weathermen love this because they build satellites that observe at 6 microns. And if you've ever gone to NOAA website or Wonderground or whatever, you might have seen water vapor maps that tell us where the storms are, where all the water moisture is. So there's a big band of moisture blowing up through northern Mexico and Texas. Southern California is a little drier. There's a big band out over the ocean just north of the Hawaiian Islands where there's very little water vapor, and so you see all the way down to the surface of the Earth. That's why it's so dark. So weathermen like it, astronomers on the ground, not so much. And then finally, the sensors themselves. It sounds a little funny, but if you have a sensor that's sensitive to temperature, the sensor has to be colder than the stuff it's trying to detect, otherwise it detects itself. So we have to cool things in the infrared to very cold temperatures, and if you do that in the air freezes on your detectors and that messes everything up. There are also some false signals that are generated by the detectors, and so we have to get them even colder. Most of the 3 of the instruments on James Webb need to be cooled to 40 degrees above absolute zero to work. MIRI, the instrument I work on, needs to be cooled to about 6 degrees above absolute zero in order to work. So all those things together, the radiation of room temperature things, the atmosphere, and just our sensors, really does mean we want to put our infrared telescopes up in space so we can see what's going on. So to address the scientific questions, to make things work in the infrared, we're building the Webb telescope. So Webb is a 6-meter infrared optimized telescope. You'll notice the primary mirror is coated with gold rather than silver. Gold is actually a better reflector of infrared wavelengths than silver is. It has 4 instruments that cover 0.7 to 28 microns. Now, I know that doesn't mean much, but the reddest color your eyes can see is right about 0.7 microns. So James Webb takes off right where your vision fails, so into the infrared past that. Webb is a partnership between NASA, the European Space Agency, and the Canadian Space Agency. None of us can go it alone. We got to work together on this stuff. And it's going to be launched on a European Ariane 5 rocket. Now, you saw the picture of Webb sitting in the clean room at Goddard, all unfolded. That does not fit in any rocket currently in production. We've got to fold it up. And so you'll notice that 3 of the mirror panels on this side and 3 on the other side fold back. That secondary mirror that's supposed to be out here is up on top. The sunshade is folded up like, kind of like butterfly wings tucked in there. And so James Webb Space Telescope is an origami telescope. It's got to unfold. After it launches, the fairing separates, things begin to expand. So first we got to get our solar panels out so we can get power. There's a lock on the antenna. We pitch the telescope a little bit and we do some course corrections. A long course correction, apparently. Pitch back a little bit. We extend our antenna so we can establish high-speed communications with the Earth. It's all low speed up to that point. Another little course correction. Then we begin to unfold stuff. So first we're going to start with that sunshield. So first the structures that actually hold the sunshield fold back from the telescope. We do the front side first. Then the backside comes down. Now to help the telescope clear that sun shield, the telescope itself is actually on a tower that separates it from the rest of the spacecraft, and that tower has to extend about 6 feet in order that nothing in that sunshade touches the telescope. So that was that tower deployment. The covers come off the top of the sun shield. This is all packaged like some little tinfoil wrapping thing. We release a couple of locks, and then these booms deploy that stretch out that sun shield from where it's folded up in the center. So we do one side first, then the other side. Now that sun shield is actually 5 layers of material. And it's very important that those 5 layers separate because on the sun side, the temperature of this first layer is about room temperature, about 300 degrees above absolute zero. But the telescope needs to be 50 degrees above absolute zero, so this top shade has to be 50. So if there's any touching in between, it will heat up the next layer and we won't get cold enough. So that's one of our big concerns. Now we're getting ready to release the secondary mirror. And so you can see the structure starting to move. Then the secondary mirror, which is here, swings forward and moves to the front of the primary mirror. And then finally, the side wings of the telescope primary mirror move into position. Here comes the other side. That whole process takes 2 weeks. So the Mars guys had 7 minutes of terror while they were trying to land a rover on Mars. We got 2 weeks of terror waiting for our telescope to deploy. After it's fully unfolded, then begins the long process of the whole telescope has to cool down. Our instruments have to cool down. Until everything is settled, we've made sure everything works. We do our calibrations. It's 6 months after launch before we're ready to start taking scientific data. So it's a long one. Another thing different between Webb and Hubble is where it's located in space. Hubble actually orbits the Earth just a few hundred miles up, so it actually orbits the Earth every 90 minutes. And some evenings when Hubble goes overhead, you can watch it streak across the sky. Webb is going to be located 1 million miles from Earth, 4 times the distance of the Moon. There are 5 spots between the Earth and the Sun where the gravity of the Earth and Sun balance the tendency of the spacecraft to go running off on its own. These are called Lagrange points, after the mathematician who discovered them. The second Lagrange point, nicknamed L2, is actually a really nice place to put spacecraft because our sunshield will always shield the Earth, the Moon, and the Sun from shining on the telescope. We've sent a number of spacecraft out there. Webb will be joining the collection. So I mentioned Webb has 4 instruments, so I'd like to describe them very quickly. NIRCam is our near-infrared camera. It's primarily to take pictures of things. It has a tool called a coronagraph, which I'll explain in a second, and it does some very simple spectroscopy. So the top is some images from the Hubble Space Telescope with the wide field camera number 3, which has limited infrared capabilities. If we were to image the same galaxy with Webb, not only do we see fainter galaxies around it because we have so much more collecting area, but we begin to see some of the spots that are just sort of fuzzy in the Hubble image. And again, this is a simulation. We don't have anything yet. But these spots, might be regions where stars are being actively formed, or they might be remnants of those little galaxies that collided, that merged together to form a larger galaxy. But that's the kind of stuff we want to find out with Webb. And so it will be a great tool for examining these very early galaxies. A coronagraph is an instrument that blocks the starlight. So whatever's right in the center of the coronagraph, the light from that gets blocked. So we'll put a star right in the center. And so where the star was gets blocked out, so we don't see the starlight at all. But that allows us to see other structures around the star that normally are lost in the glare. The star is so bright that we can't see these things. This is a star called Beta Pictoris, and we saw this kind of disk structure. And we said, in our solar system, we have a similar sort of thing. We have zodiacal light, which is dust near the Earth that on a good dark night out in the desert, you might be able to see as a band of light. Well, this is much thicker than in our own solar system, but we said, hey, that's kind of a signature of a solar system. Wonder if there are planets in there. Well, a few years later, after our coronagraphs improved, we have a coronagraph which is much tighter, and we noticed there was a spot next to that star. And it turned out they imaged it again 6 months later, and that spot was on the other side of the star. Turns out this is a planet. So it has, I don't remember what the period is, some number of years. But we saw it in part of its orbit, and it'll go around for quite a while before it gets all the way around. But with these coronagraphs, we can actually take direct images of planets. So if the planet is far enough from the star, we might be able to detect it. And so that's something that people are very, very eager to do with the Webb telescope. NIRSpec is our big spectrometer. A couple interesting things about it. It has 2 ways of making a spectrum. It uses microshutters, and it has an integral field unit, which are really technical terms, but I'll explain what they mean. With a microshutter, it's like shutters that you put on your windows. You have all the slats, and you can open some of the slats if it's maybe broken to let in light from one slat and not the others. So if we have an image of galaxies on the sky, we can put the microshutter array in front of them, and then we can choose which shutters to open so that we get spectra of just the galaxies that we're interested in. So here we've opened a few shutters, and maybe that one corresponds to that galaxy, this one to that one, and that to that. I don't know. The drawing wasn't very good. But the point is we can get spectra of those 3 galaxies at exactly the same time. In fact, we can do up to 100 at one time, which when you have a big, expensive telescope, it's good to do as many things at the same time as you can. So this is one way to get information on many different objects. So that's what we call the microshutter array with the spectrometer. The other thing, the integral field unit, takes a tiny square of sky and slices it up. So it uses a special mirror that has these steps on it so that the top slice gets put into the spectrometer on the left edge, the next slice next to it, and so forth. So we spread these 6 slices out and get the spectra simultaneously. And so it's another way to get information over a larger area all at one time. One of the neat things you can do with this is if you put such an integral field unit on a galaxy, remember I talked about red shifts and blue shifts? You can see those Doppler shifts in the stars in the galaxy. And so we can actually tell which way the galaxy is rotating. This top galaxy, the lower end is coming toward us, it's blue shifted. The top end is moving away from us from the redshift. This galaxy is sort of the same thing. So in both of these galaxies, we see strong signatures of rotation. We can tell how fast it's rotating, which tells us how big the galaxy is. And so it's an important tool for understanding those galaxies, at the far fringes, understanding how they formed. The fine guidance sensor near us is actually sort of two instruments in one. I should have said NIRCam was built by the University of Arizona, and NIRSpec was built by the European Space Agency. FGS NIRIS is built by the Canadian Space Agency. It serves as the fine guidance sensor to help us actually point the telescope and lock onto stars. The near-infrared imager and slitless spectrograph is sort of a specialized imager and spectrograph. It doesn't duplicate what the other 2 infrared instruments do. One of the neat things that it does do is it has the ability to take spectra of the same fields in 2 different directions. So there's a pair of stars here, and in this image, the starlight is spread horizontally. The same 2 stars are over here. In this way, the light is spread vertically. What's the big deal? Well, if you're getting spectra of all these objects at the same time, it's inevitable that 2 stars, the spectra overlap each other one direction, but when I get the spectra in the other direction, they're well separated. And so one image or the other will give me a good spectrum of the sources that I'm interested in. Okay, finally, the 4th instrument, this is MIRI. This is the instrument that we've been working on here at JPL. The other 3 instruments all work from about 1 to 5 microns. MIRI works 5 to 28 microns. Because we're the only instrument that works at these wavelengths, we have to do all the things that the other instruments do. So we have an imaging capability, we have chronographs, and we have a spectrometer. I forgot to point out, at JPL, we were responsible for the detectors. And every image of MIRI that I can find on the web, they always hide my detectors. So gratuitous self-promotion. This is what one of the JPL LED detectors actually looks like. Yes, that's me. You can tell by the eyebrows. This is Kalyani Sukatmi, who was, until recently, our project manager. So this was early on when we first delivered the detectors to be bolted onto the rest of the instrument. A few words on why we want a mid-infrared instrument in the first place. If we can learn a lot from the near-infrared instruments, why do we need a mid-infrared instrument? Near-infrared, we detect mostly the ultraviolet light from those galaxies that are very far away, that have been redshifted from ultraviolet to the near-infrared. Well, the visible light from those galaxies gets redshifted into the mid-infrared. So if we want to study the normal stars in those really far away galaxies, we need to look at them in the mid-infrared. We see mostly atoms and molecules in high energy conditions, high temperatures in the near infrared. We see molecules in lower energy conditions in the mid-infrared. If we look at stars that are forming planets, we see the more mature stars in the mid-infrared. If you want to see the very young stars that are still themselves in the process of forming, we see that in the mid-infrared. And finally, if you're looking at the planets themselves in the near infrared, we tend to see the really hot stars that are close, or really hot planets that are close to the stars, things that are 1,000 degrees, someplace we definitely don't want to visit. If you want to study planets that are more room temperature, more like the Earth, then we'll want to look at those in the mid-infrared. And there are many, many more reasons, but these are a few of the things that are important. A little bit more about MIRI. All the other instruments were built, or at least there was one organization responsible for the instrument. With MIRI, it was a 50-50 partnership from the beginning. JPL, it was responsible for half the instrument, the detectors, the electronics to run the detectors, and the cooler that gets us down to that 6 Kelvin temperature were all the responsibility of JPL. 24 astronomical institutes in 10 different European countries were responsible for the optics and the structure of the instrument. And when this was first proposed to our senior management here at JPL, they all shook their head and said, it's never going to work. I'm pleased to say it worked actually very, very well. We had great people on both sides of the pond, so to speak, and I think we have a really great instrument. What do I want to look at myself? In the introduction, Mark explained that I'm interested in star formation. I do have a little bit of time of my own on Webb where I can point it at anything I please. And so what do I want to look at? Well, I got some questions. I'd like to understand how binary stars form. About half the stars that you see in the nighttime sky are actually binaries, two stars that are orbiting each other. When we look at very young stars, the stars that are still in the process of forming, it's more like 80 to 90% of them. So why do stars form as binaries and then lose their companions along the way? So I'd like to understand a little bit more about those binaries. Also, I mentioned that planetary nebulae with that kind of wing, that low wing-shaped structure, generally need binary stars to form structures like that. So the common theme is binary stars. So I'd like to know a little bit more about what shapes the planetary nebulae. This is a very young star. It's actually a triple system. So there are 3 stars here. The bluish color of these 2 stars generally indicate that they are hotter. They might even be almost normal stars. Whereas this yellow reddish color, because this is a mid-infrared image, this we would normally interpret as a very young star. Well, if they're gravitationally bound to each other, they had to have formed at the same time. So how is it that you can have 2 older looking stars and a younger looking star? If you get crude spectra of these stars, the 2 top sources are the white and red curves up here. They're kind of normal and flat. This is relative to a normal star spectrum. So they look about normal. But this yellowish star has much more infrared radiation than getting toward the visible. So it's much colder in apparent temperature. But the important thing is that the solid lines were data that was taken at one period of time, and then the dashed lines was 3 years later. So these 2 stars stayed roughly constant, but this star actually, not only did it get brighter at short wavelengths, the temperature actually got apparently hotter. So what's going on? So one of the ideas is that that gas and dust that forms the stars is still streaming onto that star, and as it falls onto the star, it heats up and causes the changes in temperatures and so forth. So with Webb, I'd like to study that a little bit more. I should be able to see material actually around the star, perhaps flowing into that star. On the planetary nebula side, this is a different planetary nebula called the Egg Nebula. The image on the right was taken with Hubble. And so it shows these neat lobes that are blowing out from a star that you actually can't see. There's a big disk of dust around the center that's absorbing all the starlight in the center. This image was data that I took with the Keck telescope with my mid-infrared camera on the ground, where it's really hard to see stuff. But even so, you can trace the lobes of that planetary right down to the center. We still don't quite see the central star. That's just a blob of dust. That's not the star itself. But it's hard to see here, but there's also sort of a halo around it where that warm dust in the disk is glowing, emitting its own light. This is another planetary nebula. This one looks a little normal. It's kind of round, and it's a little bubbly in the center, but it's fairly unremarkable. But when we looked at this planetary nebula with the WISE All-Sky survey, we discovered that it had a pair of concentric rings around it. So how did that structure form? This also requires a binary star to shape it. And so we're still trying to understand just how does that work? What makes those shapes? And so I'd like to use Webb to get information about those rings, what they're composed of, what the energy situation is like, to see if we can understand a little bit better what's going on with that planetary nebula. Okay, what's Webb's status and what's up next? So MIRI was the first instrument delivered. It was installed into the Science Instrument Module in 2013. And I do have to point out the detectors are on the back side, and so you can't see them again. All the instruments were on board by 2014, within the year after that. And then it went through a number of rounds of testing. We wanted to make sure that the instruments all made it to the Goddard Space Flight Center in one piece. We wanted to make sure that the computers that are going to run the Science Instrument Module were actually able to control the instruments. And they went through a number of tests to make sure they'd survive launch and all that sort of stuff. Just earlier this year, you may have seen some of these pictures. The telescope itself was completed. And then just a few months ago, that instrument module in the previous picture was lowered onto the backside of the telescope, so it was installed behind the primary mirror. And so that whole assembly is now ready to go through its own testing. Its next stop is actually the Johnson Space Flight Center down in Houston, where it will go into Chamber A. This is a huge vacuum chamber that was used during the Apollo missions, where they'd test the Apollo spacecraft. And in fact, they would throw people inside there, the astronauts, because they needed to train to work in a vacuum environment. So it's been repurposed to test the Webb telescope. This is what the telescope will look like inside the chamber. And then there are a bunch of light sources and other instruments up on the top to measure the properties of the optics of the telescope to make sure they're what they're supposed to be. We can't refurbish Webb, so it has to work the first time. So after the testing at Johnson, the telescope will make its way to Northrop Grumman, right down here in Redondo Beach. The spacecraft, that propulsion system and all that stuff, and the sunshield will be bolted together. The telescope will then be connected with it, and we'll have a completed observatory. In early 2018, there'll be some short, it's probably still a couple of months, but a short functional test to make sure everything is ready to go. And then in October 2018, hopefully, we launch. And with any luck, you'll invite me back in about 3 years to give you a few of the first results. So that's it. I hope you learned a little bit, and I'd be happy to take questions. So if you do have questions, please come up to the microphone.
Did you say when Webb goes operational, Hubble will still be in operation?
We hope so. The only thing really limiting it is whether any of the gyroscopes in Hubble break and whether there's enough funding to actually operate both of them at the same time. But we think we'll get at least a year or two of overlap, at least fingers crossed. Yes?
Thanks for a great talk. I was interested in learning more about the 6 Kelvin requirement for MIRI. Yes. And how you plan to achieve the 6 Kelvin requirement and how long it has to be at that 6 Kelvin temperature range when you're taking measurements?
Okay, so all the other instruments operate at about 40 Kelvin, and we can get to that temperature just based on cooling of space. We call it radiative cooling. MIRI, to get down to 6 Kelvin, actually requires a cooler, a cryocooler. Comparing it to your refrigerator in your house isn't really fair, but it's kind of like the refrigerator or freezer in your house. It is a mechanical cooler, so it should last for a very, very long time. In fact, we think the final limit to the lifetime of Webb is actually the propulsion, our ability to steer. If nothing breaks, if everything survives launch, everything should be able to go at least 10 years. That's the goal. 5 years for sure, hopefully 10 years, maybe longer. But it is a mechanical cooler that gets us to 6 Kelvin. Right?
Come through. Watch out. Hey, we're moving now. Yay. Here we go. Hang on. To the moon. Whoa! This is wonderful. I love exploring. I've never seen that before.
I want the big one.
No fair! I saw it first.
I'll race you.
Ah, you're on.
You'll never catch me.
Come on, guys. Wait for me.
So many places to go.
Huh? Yeehaw!
On your left.
Hey! Here we go. Is everybody ready?
Yeah.
Season's greetings.
From NASA.
Welcome to NASA Goddard Space Flight Center. I'm Michelle Thaler, and for the next few hours and the next few weeks, I'll be your host on the beginning of a new adventure to find our place in this vast cosmos and our role in a story that stretches back to the beginning of time. Approximately 30 days from now, NASA and our European partner ESA will launch a new observatory into space of such ambition, inventiveness, and boldness of vision that it promises the arrival of a new era, an entirely new view of our universe. This is the James Webb Space Telescope, and this new universe is almost here. Standing here on the shore of the cosmic ocean, we're about to take the next step on a journey that is as old as humanity itself. From the first time we looked up at the stars and wondered what they were, to the advent of new telescopes and new technologies, Webb is next in line to take us closer to an understanding of where we are, where we came from, and also where we're going. Today we'll start by talking about the main science goals of the Webb telescope. And to dive right in, I'm joined by Greg Robinson. Greg Robinson is the program director of the Webb telescope. So Greg, I'm going to put my mask on here as I get a little bit closer to you. You're here representing a very large team today, aren't you?
Hi, Michelle, and thank you. Yes, I'm here representing a very large team. First, I want to thank all of the people joining us today from around the world for going on this long journey with us. And it's been long, and it's a long ways to go. Also, I want to thank the more than 10,000 people who've worked on Webb to make this possible, including our European Space Agency partners and our Canadian Space Agency partners, and across 29 states and 14 countries. So a lot of people went into making this possible. And just to give you a little update, a little status, we completed INT in Southern California, north of Grumman, back in the summer. We pushed the boat off from the port in September, late September, and it arrived down in French Guiana in Kourou on October 12th. Since then, we've processed the spacecraft. It's getting ready. In parallel, Ariane Space been processing Ariane 5 rocket. That's getting ready. And in a few days, we will start fueling the spacecraft. Shortly after that, we'll move over to the final integration facility, mate it with the rocket, and get ready to move out at L-2 so we can launch on December 18th. So we're looking forward to that, a lot of really good progress. And that's not the end. Right after launch, the Space Telescope Science Institute in Baltimore will take over for mission operations, and we'll have about 6 months of commissioning to get the spacecraft ready for those first big images we've talked a lot about, and you will hear a lot about that from the scientists. So looking forward to this, and we're getting very, very close. So stay tuned, and I'm just extremely, extremely amazed.
It is so wonderful to have you here. Thank you so much for joining us today.
Thank you, Michelle.
So obviously the James Webb Space Telescope represents thousands of people that have worked on this mission for a very long time. But if one person really had to be the parent, the father of the James Webb Space Telescope, it would be my next guest here, John Mather. So John, thank you so much for joining us today.
Thank you. I'm smiling inside my mask.
Absolutely.
I am indeed proud to be here as one of the many fathers and mothers of this telescope. Do you know that this telescope is so powerful that if you were a bumblebee hovering 240,000 miles away, which is the distance of the Earth and the Moon, we would be able to see you. Not if you're on the Moon, but at that distance of the Moon. So what are we going to do with this great telescope? We're going to look at everything there is in the universe that we can see. We want to know, how did we get here from the Big Bang? How did that work? So we'll look. We have ideas, we have predictions, but we don't honestly know. So the way we think it is that the universe is expanding. Distant galaxies are rushing away from us at immense speeds, roughly proportional to the distance. Divide the distance by the speed, you get the age of the universe. It's about 13.8 billion years. Well, what happened before that? What was it like then? Well, we think the early universe, before there were galaxies and stars and planets, was very hot and very dense. And it was a little bit lumpy, how would you know that? Well, NASA launched a satellite called the Cosmic Background Explorer satellite on this day 32 years ago. And we measured. We saw that not only is this Big Bang story about right, but it has the primordial seeds that would grow up to become galaxies. So we know this story is probably right. So now we have movies that we can show that say what the computer thinks might have happened if this is a correct story. So that's our idea. Now we want to check it by observing everything we can. So what we think happens in the very early times, small galaxies were formed very quickly, and then the gravitational forces pulled them together and they got to collide with each other and get bigger and bigger, and then the galaxies merged with each other, and as that happens, the black holes in the middle, if there are any, merge together too. That's one of our big questions: where did the black holes come from? Then after that, the universe just continues to expand and galaxies rush apart, and we're here wondering, how did this all happen? So we want to look at those first galaxies growing. We also want to look at things nearby to us, clouds of glowing gas and dust where we know that stars are being born today. So they're beautiful to look at, and astronomers would say, well, what's inside? Well, we look at them and they're dark. They're dark areas of the dust is obscuring our view of those earliest times when the stars are growing. But we can see them with infrared. Infrared light will go around the dust grains instead of bouncing off. So we can see that with the Webb telescope, and that's one of our top goals, to see how stars grow with their young planets. So that's what we're going to do. We will be looking at the solar system too. We'll be looking, excuse me, that was the wrong word. We're going to be looking at the various instruments that excuse me, I'm going to show you the wavelength range, where we want to show how the Webb telescope fits in between the different instruments that we've had before. We show different kinds of light waves on the picture. There are short wavelength ones and long wavelength ones. The Hubble telescope observes the light you can see. It observes ultraviolet, which will give you a sunburn, gives you a little bit of infrared, but the Webb telescope goes next. It observes wavelengths that you can see, but it goes all the way out to infrared of 28 microns wavelength, which you can't see at all. And then that complements the Spitzer Space Telescope that's been up there for a long time and has now finished its job, and it went out to even longer wavelengths. So that's what we're flying, what we're looking with. We are going to look at all the objects in the solar system. The objects in the solar system beginning with Mars and going all the way out. So we can't look any closer to the sun because the telescope would get too hot. But we can look at Mars, and it's moving, of course. We have to be able to track a moving object. We'll be looking at Mars and satellites like Europa, which orbits around Jupiter. Europa has an ocean, and it's covered with ice. And we know that because we sent a satellite to probe that one. And in between the blocks of ice, there are water jets that come out. And we're going to send a mission out there to fly through those water jets to see what's that ocean like. Maybe it has molecules in it. Maybe molecules that might be signs of life. That would be really interesting. We'll be looking at Titan. Titan is a very cold but very large satellite of Saturn. It's so cold that it's able to hold liquid oceans of methane and ethane. And it has clouds and rain and rivers and lakes. And we're sending a satellite out there with a helicopter to fly around and explore that one. So we'll be looking at all of these things way out there, everything from the most distant galaxies, the first galaxies that grew in the early universe, to everything close to home. And we'll be looking at planets around other stars. Planets around other stars, well, that's hard to see them. But once in a while, a planet will go in front of its star, and the star will blink a little bit, and you say, oh, I know there's a planet there. Our special capability here is with some of the starlight will go through the atmosphere of that planet on its way to our telescope. We can analyze that atmosphere, if there is one, and say what's in it. Molecules of various kinds, maybe especially water, which would be really interesting to see that there's a wet planet out there that might be a little bit like home. So we have altogether 4 instruments to examine all these things. There is a near-infrared camera that comes from the United States. There's a near-infrared spectrograph, which is mostly from Europe with some United States parts. There's a mid-infrared instrument, which is a partnership between Europe and the United States. And there's the far-infrared, the near-infrared imaging slitless spectrometer from Canada, along with a fine guidance sensor, which we use to make sure that we're going to get sharp pictures. All of these are complete, they're all working, they're all in the observatory ready to fly. So we're thrilled to think about what we're going to see with them.
Oh, that's wonderful, John. I know you've been with us from the mission. It's such an honor to have you here today. Thank you so much.
Thank you.
For our next guest, it's really important to remember that this mission has been an international partnership from the beginning. And so representing the European Space Agency, I'm very pleased to have with me Antonella Nota. So thank you so much for joining us, Antonella. Tell us a bit about the European Space Agency contribution to this.
Michelle, good morning. It's such a pleasure to be here. I want to tell you that at the European Space Agency, we're absolutely thrilled that we're part of this magnificent mission with our colleagues at NASA and the Canadian Space Agency. It's an international partnership that has been built over decades of work on the Hubble Space Telescope, and we are positive that there will be future collaborations in the future, because that's the only way to do big, ambitious missions like the James Webb. So the contribution that ESA provides to the Webb mission are threefold. First, the launcher, the Ariane 5 rocket, will depart from the spaceport, European spaceport in French Guiana, and will deliver this powerful telescope to L2, where it will start the journey to explore the universe. The other 2 contributions are instruments, the near-spec instrument and the mid-infrared camera and spectrograph. Talking about the Ariane 5 for just one more second, the Ariane 5 is actually an impressive rocket, very powerful, is operational since 1996, has more than 100 successful launches, including some to L2 like Herschel and Planck. But coming back to the instruments, what kind of science will these instruments do? So before we talk about the science, I think it's important to remember that Webb will be a spectroscopic telescope, most than everything. Of course, we'll take beautiful images, but spectra will be the bulk of the science. And why? Because spectra is what tells us what the objects are made of. While images, they're beautiful, they are spectacular, but they tell us the morphology, what the object look like. But astronomers want to know the composition. So to do that, they need to split the light in its components. So spectrographs do exactly that. Like rain droplets split the sunlight in its colors when we see a rainbow after a thunderstorm. The spectrographs will produce spectacular information for astronomers to use, because while an image is, we say, is worth 1,000 words, spectra are, for astronomers, are just worth 1,000 images. What kind of objects will they look at? This is, we're interested to know. NIRSPEC will observe for almost 40% of the time during the first observing cycle. And we look, one of the things that for sure NIRSPEC will look is the very distant universe. If you remember the Hubble Deep Field, those faint galaxies, well, NIRSPEC will be able to take spectra of them. And because of the innovative design, we'll be able to take 100 spectra at the same time in one single exposure, extremely efficient. So we can't wait to see the first spectra for NIRSPEC. MIRI, the mid-infrared camera and spectrograph, will look through the dust, deep into the dust, and will, for example, see the emerging stars, the baby stars. One of the key questions in astronomy is still how stars form. And MIRI will nail it, because we'll be able to observe baby stars as they emerge from their cocoon the first million years of their life. Like, for example, in a star cluster like this, NGC 602, that is full still of dust. And we know that there are thousands of baby stars there. We just cannot see them. And finally, I want to conclude saying that the European community is extremely engaged, committed, and ready to go. We are just waiting. If we look at the map of Europe, every single dot is an institution or a center that has played a role in Webb. And so Webb is pretty much in every single ESA member state. And we collectively will do the countdown together, and we can't wait to see the first data.
That's so exciting. Thank you so much for joining us. I'm glad to know all of our European friends are waiting for the launch too. So,
absolutely.
Yes. Well, keeping on the theme of the international collaboration for the James Webb Space Telescope, joining us right now from Montreal is Sarah Gallagher, representing the Canadian Space Agency. So Sarah, excellent to have you here today. Tell us a bit about Canada's involvement in the Webb Telescope. Oh, there we go.
Thank you so much, Michelle. I am delighted to be here, and we are so proud to be a partner for this exciting mission. As we've heard, Canada is contributing two important elements to the Webb Telescope: the fine guidance sensor and the near-infrared imager and slitless spectrograph, which we affectionately call NIRIS. And these two instruments are combined into a single structure within the telescope. These two contributions showcase our excellent industrial capacity to support space astronomy. The fine guidance sensor will be used during all scientific observations made by Webb. By using the star fields to determine exactly where the telescope is looking, the system will enable the pointing that is needed to give us the exquisite images that we are so looking forward to. The Canadian astronomy community is so excited and fully engaged in the opportunity afforded by our participation in the Webb Telescope, and we have plans for lots of exciting scientific explorations. Some of the first studies will include observations of the regions around very massive stars to study how these powerhouses affect their environments. And these studies will happen really early in the observing plan with some of the early science observations. As we get closer to launch, we feel growing enthusiasm in the community for the science that is coming. The interest in our community is broad and touches on a huge variety of research topics in astronomy. This includes detailed examinations of exoplanets, the worlds around other stars, the search for the first light sources in the universe, the formation and evolution of galaxies, the life cycles of stars, and studies of small bodies such as icy moons, asteroids, and comets in our own solar system. In fact, a Canadian team will focus their studies on the atmospheres of exoplanets to determine their compositions and temperatures. Some of the research team's targets are rocky planets like the Earth. The team hopes to make the very first detection of an atmosphere on such a planet. This could give us clues as to whether or not these planets are habitable. Looking towards the far distant universe, and thus far back in time, another Canadian team will study some of the first galaxies ever formed and galaxies gathered in dense neighborhoods called clusters. They will collect images and spectra from these galaxies at different times over the history of the universe to help us better understand how galaxies evolve over time. These two programs I've just described both use the Canadian-built Webb instrument near us. We are also really pleased and so proud of the excellent scientific leadership shown by early career Canadian astronomers who are leading many of these projects during the first cycle of observations. This interest from the next generation shows the vibrancy of our community. Their work will help discover other worlds, learn more about the life cycles of stars, and paint a picture of the early universe and of galaxies as they evolve through time. We are truly looking forward to this new era in space astronomy, and we just can't wait to get started.
Thank you so much for joining us, Sarah. Great to have you. For our next guest, one of the most important places in the James Webb Space Telescope family is the Space Telescope Science Institute. And I'm joined by Klaus Pontoppidan. Welcome, Klaus.
Thank you so much, Michelle.
So tell us a bit about the involvement of STSCI and your involvement with James Webb.
Sure. So as we've heard, we're about to go on this amazing journey of discovery. And we really mean discovery, because Webb has this raw power to reveal the unexpected. Right? We can plan what we think we're going to see, but at the end of the day, we know that nature will surprise us more often than not. So this new scientific territory, we call it discovery space, and Webb, being a flagship mission, is able to unravel this discovery space. So the way you do that is you have new capabilities, new technological capabilities, and Webb has that in abundance. For example, Webb will be able to see in the infrared phenomena, stars, galaxies that are 100 times fainter than what was previously possible. And so we just can't predict what's there. And we sort of know how this goes because we can look back to the Hubble Space Telescope, a previous flagship. When Hubble was launched in 1990, we had not discovered dark energy, this mysterious force that pushes the universe apart, but Hubble discovered that. We didn't know of any exoplanet in existence, but today we know thousands of exoplanets, and there are more specific discoveries as well. For example, Hubble discovered 2 new moons of Pluto that could help the New Horizons probe as it visited that world a few years ago. And we think Webb will be no different in that sense. There are almost 400 individual investigations already lined up for the first year of science with Webb, and these investigations represent thousands of scientists from all over the world. And some of those programs will address questions that we did not know we had when Webb was first designed, but it has the power to address them. For example, Webb will look at colliding neutron stars, like these cataclysmic collisions, and the debris field they create, we think now, creates some of the heavy elements in the universe, some of the heavy metals, most prominently gold, including the gold that is covering the mirrors of Webb itself. Webb will look at a lava planet where we think it might rain lava, and Webb will determine if that is really true. And finally, Webb will look at a new phenomenon that is interstellar comets. So bodies from other solar systems that at one point in the past were ejected, traveled through the universe for maybe a billion years before, for a brief moment, it zipped through our solar system. And Webb is able to quickly point at them and understand what they're made of, to tell us if other solar systems are made up of the same materials as our own Earth and Sun. And so we think Webb will probably also reveal new questions for future generations of scientists to answer, some of whom may not even be born yet.
That's absolutely wonderful. Thank you so much for joining us, Klaus.
My pleasure.
All right then. So for our last guest today, we have Amber Strawn. And Amber Strawn is the Deputy Project Scientist for Communications here at NASA Goddard Space Flight Center. And Amber, you're one of my absolute favorite storytellers, an astrophysicist. I think you see the Webb telescope as part of an incredible narrative about our place in the universe, correct?
Absolutely, yeah. I mean, my own area of research is how galaxies change over time and how they form their stars and black holes. And there's a lot about this overall process that we still just don't understand. We do know that very distant galaxies are much different than galaxies in the nearby universe that we see today, but we're sort of missing this piece of the puzzle. We haven't yet seen those very early galaxies in the early universe. And so it's like we have this 13.8 billion year story of the universe, And we're missing this sort of a few key paragraphs in the very first chapter of the story. And so what we're really trying to do here is figure out how to put all those pieces of the story together and learn more about that whole process. And of course, JWST was designed to help us find those first galaxies. And of course, galaxies are the homes of stars, and stars are the homes of planets, and planets are the cradles of life. And this telescope is definitely our next big step in our search for potentially habitable planets other than our own. So very exciting. You know, JWST in general was designed to answer some of the biggest questions that we have in astronomy today. And one of my favorite things about astronomy in general is that it really gets right down to our big questions. Where do we come from, and how do we get here, and are we alone? And these questions are more than just arcane science questions. They're questions that get to the heart of what it means to be human. And you know, Klaus mentioned this exciting prospect of maybe we'll find things that are unexpected. And to me, that is the most exciting part of this whole mission, this idea that there are surprises out there in the universe. And I think we'll find them. It happens every single time we launch a big, bold telescope into space. And JWST is the biggest and boldest yet.
Absolutely. Thank you so much for joining us, Amber.
Sure.
We'll talk to you more later.
Thank you.
So before we can learn about the origin of the universe, we have to get the Webb telescope off the planet. And that's a job for a big rocket, one of the largest, the Ariane 5, and it launches from the Guyana Space Center. Located in Kourou, French Guiana, it's a tropical facility, but it's also a gateway to the stars. Few spaceports on Earth present soundscapes that include the roar of rockets, followed by the sounds of a tropical jungle once the rising spires of fire disappear above the clouds. Once Webb's Ariane 5 leaves the launch pad, flight control transfers to the Mission Operations Center in Baltimore at the Space Telescope Science Institute. It's here where mission managers will not only control the spacecraft, but also gather data from the telescope's scientific instruments. So what we're going to do now is take a quick break, and we're going to reset the stage to take live questions from the audience and also from the media. So if you'd like to join us with questions, you can go to #NASAWeb. And we'll be back in just a few minutes. We're here at the Goddard Space Flight Center. I'm Michelle Thaller. Please come and join us again.
Our universe is a wild and wonderful place. In NASA's Curious Universe podcast, NASA is your tour guide. Join astronauts, scientists, and engineers on a new adventure each episode. Investigate black holes. Spend a day on the International Space Station and meet the experts behind the revolutionary James Webb Space Telescope. Find NASA's Curious Universe in your favorite podcast app or by visiting nasa.gov/podcasts.
What's out there? Let's find out. The James Webb Space Telescope Augmented Reality app. Whoa! Check out the most extraordinary scientific instrument ever designed in your own space today, only from NASA.
Welcome back to Goddard Space Flight Center. This is the pre-launch briefing for the James Webb Space Telescope, and I'm Michelle Thaller. Now we have a panel of all of the guests that you heard from before, and they're going to tell us about the science goals of the James Webb Space Telescope, and they'll also be taking live questions from the media. So in order to get this started, I will now ask the operator, do we have questions from the media to begin with?
Yes, we do. Our first one is from Elizabeth Howell. Your line's open.
Thank you very much. This is probably for John. So among the early observations, the early release science programs, have you selected the ones yet that are going to be happening first or very quickly after first flight?
John, did you hear the question?
I think they asked what are we going to do first?
That's right, yes.
Okay, yes,
Exactly.
we have indeed
Yep.
planned the entire, let me get this off.
That's right.
We have indeed planned the entire first year of scientific observations, and we know the highest priority things. We have chosen some early release science programs that will be announced immediately after they're observed. So we'll be giving you the data as soon as we have them for those great pictures. And they cover a very wide range of topics, all the way from the solar system to the very first stars, galaxies, and black holes. Everything.
Excellent. Does that answer the question? We're all good?
It does. Thank you.
Do we have any more questions from the media?
And thank you. Once again, to ask a question from the phone line, that would be star followed by number 1. Again, that's star 1. Please unmute your line and record your name clearly as prompted. And our next question is from Stephen Clark. Your line is open.
Hi, Stephen Clark, Spaceflight Now. I just wanted to follow up on the previous question, if I could. If someone, maybe Amber or John, can talk about the plan for releasing the first images. Exactly when those will be released. Will those wait till after commissioning is over, or will the public be able to see some images, during that commissioning process once the images are down from the observatory? And I've seen the list of the early science programs, but what will be released first of those group of early observations, or will they be released as a group? Thank you.
Yeah, so we have a wonderful plan for these early release observations, the very first sort of beautiful science images that will be released from the telescope. And those are all taken at the very end of commissioning. So this whole commissioning process takes about 6 months. And we get the final commissioning of all 4 instruments at the very, very end of that. So we'll be taking those early release observations right at the very end, as soon as those instruments are fully commissioned, and we'll be releasing them all at that same time. So that'll be happening, about 6 months after launch.
Do we have any further questions from the media?
Yes, our next question is from Marina Korn. Your line's open.
Hi, I'm wondering if director's discretion at the Hubble Space, as I'm sure you know, when I can find the ultimate beautiful.
I'm afraid that the speaker is breaking up a little bit. I'm having trouble understanding.
Oh, sorry.
Thank you. Please go ahead. Yes. Please go ahead.
Sorry. Yeah. Whether has any kind of direct discretion. Hubble Space Telescope. When Bob Williams used that, came up beautiful in the darkness. So one, any plan things or.
Klaus, I heard you. I saw you nodding. Did you get enough of that question? I'm afraid that was a little bit broken up.
Yeah, I don't know if I didn't get the whole question, but the gist I heard was a question about whether there is this director's discretionary time, just like there's for Hubble. So just to summarize, the director's discretionary time is time that is awarded by the director of the Space Telescope Science Institute, and it's for new science that appears all of a sudden that you just must do. And if we have something like that, the community can propose for it and say, we've got to do this right now. We can't wait until the next opportunity to propose for time. And then the director can look at it and say, yes, we should absolutely do this. So yes, just the same as with Hubble, there is a director's discretionary time for Webb. So I hope that answered the question.
Do we have our next question?
Marcia Dunn, your line is open.
Good morning. This is Marcia Dunn of the Associated Press. I have seen various numbers. I'm hoping to get a consensus from the group this morning. If the universe is 13.8 billion years old, how close to the beginning is Webb actually going to see? How far back does Hubble see in its very most? And is there some other telescope or device even got a better record? And what will it take, if at all, to be able to look all the way back to the first moments, minutes, hours of the universe? Is that even possible? Thank you.
I think the perfect person for that is John Mather. He's been involved in many of those missions.
Yes. The first thing that we can observe directly is the cosmic microwave background radiation, which is the primordial heat of the very earliest universe. And as mentioned earlier, it has little hot and cold spots, little bumps in it, which we think eventually grow up to become stars and galaxies. The first thing you can see with a telescope is predicted to happen about 100 million years later. And so that's the objective of the Webb telescope first galaxy search. We think they're out there. We don't know exactly what they're going to be like, but we expect to see little faint, very red or very infrared dots on the picture, and then we have to analyze them to see, is that really what we hope? That says that they really are primordial, the first galaxies, the first black holes. About 100 million years.
Okay. Do we have the next question?
Irene Fox, your line's open.
Good morning. Dr. Mather, about how far out do you expect James Webb Space Telescope to be able to detect and analyze chemicals in the atmospheres of extrasolar planets? And also, do you know of any collaborative programs with gravitational wave detectors? Thank you.
I think that was addressed to me.
That's right, yes, yeah.
So, but I think other people could answer it better. At any rate, we can analyze the atmospheres of planets around other stars because of the starlight that goes through those atmospheres. And so we have a list of, I think, 65 that we're going to observe in the first year, and they're pretty close by. We're not looking way into other galaxies. We're looking as close by here because those are the easiest and best for us to study. So I think, is that the main question?
I think so. Would anybody like to add anything, Klaus?
Yeah. Well, I can add, there was a question as well if there are coordination with gravitational wave detectors, and I mentioned that briefly earlier. So yes, indeed, there are programs that are set up so that when gravitational wave detectors see collisions of neutron stars, what we call kilonova, Webb will be able to relatively quickly go and look at the debris from those explosions and see what it's made of. And so, yeah, so there are several programs that are doing that already in year one.
Thank you. More questions from the media?
Yes, our next question is from Bill Harwood. Your line's open.
Thank you, Bill Harwood, CBS News. Two quick ones from me. You know, we all see invisible light, so everybody is familiar with Hubble imagery. Can someone talk to me a little about how the images from JWST, how infrared images, will compare with that? Are they going to be as jaw-dropping as Hubble's pictures are from a public standpoint? And secondly, to follow up on Stephen Clark's earlier question, aside from the actual first science images, will we be able to follow along as you guys focus the 18 segments of the mirror? Will we be able to kind of go along with that wavefront sensing program you guys have in that, you know, the first initial months as you're trying to get everything lined up? Thanks.
Absolutely. Amber, would you like to start?
Sure. So the question about will the images be beautiful is a great one. And the answer is absolutely yes. So this telescope is going to be 100 times more powerful than Hubble. Of course, it is an infrared telescope. And so what does infrared light look like? You can get, I always tell people when they ask this question to go and look at the infrared version of the Eagle Nebula, the Pillars of Creation. So Hubble has a little tiny bit of capability in the near infrared, and it took this stunning picture of the Eagle Nebula. So go look at that. That gives you just a little hint of how beautiful we expect these images with JWST to be. So yeah, they will definitely be beautiful.
And as far as following on, you know, to actually, you know, we actually get the news coming for all the different mirror segments and the focusing, yeah?
Yes, so we definitely plan to keep the community updated on the whole commissioning process all along the way. There's lots of different ways we'll be doing that. We'll be, of course, putting out press releases for the big milestones. We'll be having, you know, constant social media updates on our social media channels. We'll have a weekly blog. So if you go to our website, and that gets a little bit more into the technical aspects. So if you really want to learn about some of the details of what's going on in commissioning, the blog's a great place to go. So lots of different ways to keep up with what's going on during commissioning.
I know I've cleared my calendar after December 18th because we're going to be having many different briefings, many different ways that people can see what's going on and get the news out. All right, the next question from the media, please.
Our next question is from John Amos. Your line's open.
Hi, thanks very much. Greetings from London, here in the UK. The Hubble Ultra Deep Field took many, many hours to build up. I think about 8 years, something like that. How long will it take Webb to form an image 100 million years after the Big Bang? And I kind of follow up to that. Will we be able to see the black hole at that time? And if so, what kind of black hole is it be?
I know there's a number of you that can answer that question. Is somebody who'd like to go ahead?
Well,
Klaus, sure.
I can give some of it a shot here. So part of the question was how long will it take for Webb to make an extreme ultra deep field like Hubble did? So Hubble created its extreme ultra deep field. It was days and days of exposure time. Webb will do that in a couple of hours in the wavelength where there's range where there's overlap. Of course, there's this huge infrared wavelength range where Hubble could not operate, and so what we'll see there is there's no comparison. There are programs in the first year to not quite go days and days and days on end, but that will go. I think the most is 50 hours deep images. That'll be very exciting to see.
All right. Did that answer the question, or would you like a follow-up? Anything else? I think we're good?
Yeah, the black hole question.
The black hole question, that's right. Yes, that's right. So observing black holes. That's right. I know you do that, Amber, yes.
So was the question, remind me of the question.
Wait, would you repeat the question, please?
Yeah, I mean, what kind of black hole theory may exist at that time?
In the early universe, sure. So actually one of the big puzzles that we want to solve is how the giant supermassive black holes and galaxies got so big so fast. So some of the supermassive black holes at the centers of galaxies that we see in the distant universe now are much bigger than we should expect based on our best ideas of how galaxies build up over time. And so we should be able to see those supermassive black holes even further out in the more distant universe. And that will certainly help us, piece together this puzzle of how galaxies evolve over time.
Absolutely. All right, I believe we have some more questions from the media.
Our next question is Marina Korn. Your line is reopened.
Hi, Marina Korn again. Hopefully you hear me better this time. You said that Webb will indeed make use of director's discretionary. What will you do? Yes? And then a quick question for John. Some detail about how Webb is going to compete with the search for science like exoplanets. About its limitations, given Webb is not this true Earth analog.
Okay, I think
ability, like you can find that front.
I think the question is about the promise and limitations of finding an Earth analog, an exoplanet. Klaus, sure.
Right. So, if you mean an Earth-like planet, like as in an Earth size, as a distant from the sun, and with a sun-like star, Webb is not going to characterize the atmospheres of such an object. We need the next flagship observatory to do that. What Webb will do is it will characterize the atmospheres of planets around much smaller stars than the sun. It's a little easier to do, and those can still be habitable. And I think one of the key aspects of Webb is to understand whether they indeed have at least some of the properties of habitability, but it won't be a true Earth analog.
I was actually just glancing down at some of the questions we're getting from social media, and people are asking about the TRAPPIST system. So
Yes,
does Webb have plans to observe the TRAPPIST system?
Yes, absolutely. And the TRAPPIST system is a good example of planets that orbit around a much smaller star than the sun. And so we'll get excellent data of those, and there are some that are temperate. And the big question is whether they have atmospheres.
Absolutely. Okay, I believe we have one more question. Oh, follow on, yes?
Used for.
I'm sorry, you're breaking up. Could you try to repeat that one more time?
Sorry, the discretionary time, what will it be used for?
Antonella?
So the discretionary time is used in two ways. One, as Klaus said, to do something, to follow up on a recent discovery, something that cannot wait for the next time allocation. But directors in the past have also used the discretionary time to allocate it to meritorious, compelling scientific ideas. For Hubble, the Hubble Deep Field was discretionary time. So it's important to remember that there is this duality in the discretionary time, can be used for both. The community always has great input in deciding where to focus that energy and try to solve the next big question.
And thanks for adding that. The early release science program that we already talked about, that's
Yes.
also discretionary time.
Indeed.
Absolutely. All right, I believe there's one more question from the media.
Thank you. Marcia Dunn, your line's open.
Yes, Dr. Mather, I think, or anyone else. Thank you for the $100 million year mark, but what is the current record? What is the farthest back in time scientists have seen to date with what instrument? And is it possible to ever get closer than what Webb's going to do at the 100 million year mark? Thank you.
So the Hubble Space Telescope has pushed the limit to 400,000 million years after the Big Bang. So I think there is a gap the Webb has to fill between the 400 million years and the 100 million years that John Mother was talking about. So there is an entire interval in which we have a baby universe to observe, and it will be just, Webb will just present a view that we've never seen before and will be just spectacular.
And John, to follow up, is there any way to actually look farther back than the microwave background radiation?
We can only look farther in our imagination so far. We have lots of theoretical stories that we tell and calculations we make, but there's nothing to look at directly. We have evidence of very, very, very early times that are found in the polarization of the cosmic microwave background radiation, but that's not something the Webb will address. That's for other projects, which are underway.
All right, I believe we have a question. Is the next question coming from a high schooler in New York? Yes, in social media, all right. So let's see, I'm getting a number of different social media questions. All right, so this one says, okay, what makes you think you will find habitable exoplanets this time? Are more telescopes planned? So something more about the habitable exoplanets and whether there'll be follow-on missions to get better observations. I think if you want to sort of revisit that, Klaus, that'd be fine.
Well, I think the question goes that what is going to come after Webb? That's what I got from it. And yes, I mean there was just a process that it's called the decadal survey, where the astronomical community comes together and they think about what is the most important thing that we should do. And the highest priority of that survey was indeed we need to make a telescope after Webb, successor to Webb, that can actually observe Earth-like planets, Earth analogs around solar-type stars. It's very, very exciting, but it's in the more distant future.
Absolutely. So looking at some of the questions we're getting from social media, there are a number of them kind of along the same theme, and I think this one I'll direct to Greg, actually. This is a very big, complex mission. People are saying, are you nervous about launch? Are you excited? Tell us a bit about some of the testing and making sure this thing works and how you're feeling about all of this.
Well, I'm certainly excited. Nervous? No, I'm not. We have a really good team, technical team around the world that developed this telescope. They go through all of the best practices of building engineering units and testing those out before we build the flight units. We test at different levels as we build up to the telescope size, and we test as much as possible, as practical. We call it test as you fly. So we test it the same way it's going to operate in space and the way it's going to launch. And so we've done all of that, and I think we're in pretty good shape. I will say on launch day, I do get butterflies, pretty tough, and I always do. And I just expect that, so that doesn't surprise me at all.
So we've talked a bit about the first galaxies and how Webb hopes to observe those. There are also some questions involving the first stars. And could the first stars be very different than the stars that we see today? Amber?
Sure, John and I are looking at each other because he's an expert in this as well. So we think that the very first stars that formed in the early universe were very, very big, very massive, much bigger than the sort of normal stars that we see in our nearby Milky Way galaxy. And they also lived out their lives extremely fast because they were only made of hydrogen and helium and none of the heavier elements that cause stars to live slower, easier lives. And so we've never observed these first population of stars, and we certainly hope we might get lucky and see those with JWST. Not sure if we will. This is one of those things about trying to find things we've never found before, is that we certainly hope to see them. Not sure if we will. But yeah, super exciting because those first stars are totally different than our sort of normal stars. I don't know if John has any more to add.
Yeah, well, one thing about them is even with the Great Webb Telescope, you can't see them individually in their normal lives. But they do two things. One is they come in herds, hundreds or thousands or millions of them together, and then you can see them, and that looks like a new galaxy. The other thing they do is they blow up when they're old, which is not very old. About a few million years it takes to burn out. And then they become what we call a supernova, and it's as bright as a whole galaxy is today. So those are things we know we can see if they're out there. But they're hard to find. So that's our big challenge, is to find them and then study them in depth.
Absolutely. I believe we have another question from the media.
Thank you. Our question is from Irene Klotz. Your line's open.
Thanks, Irene Klotz from the HNB. Mr. Robinson, could you give us please the exact date of when the fueling is scheduled to begin and how long you think it'll last? And for anybody, could you also please provide us maybe a couple of likely astronomical targets that are likely to be among the first released images? Thanks.
I missed the very first part of the question.
I believe it had to do with, could you repeat the question? I believe it had to do with the fueling, the schedule for fueling.
Sure, just wanted to know what date is currently on the calendar to begin JWST fueling and how long it will take.
So the exact date, I don't have for you, but it will start in the next few days. Right now, hopefully before Thanksgiving, we'll see. That still keeps us on track to launch on December 18th. And as far as fueling, we just top it off like you would do in your car when you go to the gas tank. And we know we will have fueling for at least 10 years and probably much longer. Of course, we have some mandatory burns that we have to do early on after we separate from the rocket to keep us on course to L2. And we will use some burns as we need to along the way. So the fewer burns, the better for long-term life of the observatory. And so right now we're expecting many years beyond 10 years of fuel.
Thanks, Greg. I was actually referring to how long the process of fueling the telescope for launch takes. I know you said you don't have the exact date of when it's going to start, but is it like a week, a couple days, just to load JWST with its propellant?
Yeah, so fueling takes 10 days to 2 weeks from start to finish.
Thanks. And then my other question was just if someone could give us a couple of targets that might be among the first image releases. Thanks.
Who'd like to talk about first image release targets?
I think it's probably a question for Amber.
Amber?
So the first images, the first science images we expect from JWST are sort of a secret. We don't really release those to the public. We want it to be a big surprise. I don't even know what they are, so it's going to be a surprise for me too.
All right. So on social media, we seem to have some fans of Canada here, and so we're going to go back to Sarah in Montreal. So Sarah, can you tell us a little bit more about different missions that the Canadian Space Agency is collaborating with NASA on?
Yes, absolutely. So Canada has actually been collaborating with NASA from the beginning. So when Canada became the third spacefaring nation in 1962 with the Alouette space weather mission, NASA provided the launch. So the partnership goes all the way back. More recently, for space astronomy, we provided the Fine Guidance Sensor for the FUSE mission, an ultraviolet spectroscopic mission, which was actually the precursor to the Fine Guidance Sensor that was provided for the Webb Telescope. And so we partner with NASA on space astronomy, but also in other space domains. So for example, in Earth observations, space weather, and lots of other domains. And we also partner with ESA as well. So it's a long storied history. Our communities are really tight and intertwined, and we have a lot of partnerships and science projects in common. A lot of the science plans that are coming for James Webb involve international partnerships, and Canadians are active in collaborating with people from around the world. So space is truly collaborative, and as Antonella mentioned, I mean, we need to work together to achieve these big dreams. So, it's too much for any one nation. So partnership is a really important part of the endeavor.
Thank you so much, Sarah. So we've talked a lot about the first stars and the first galaxies, and there are some questions about the more close solar system observations that Webb is primed to do. I know at the opening, John, you mentioned things like Europa and Titan. The question is, can you give us some specific ideas about what they want to observe on places like Europa and Titan?
Well, sure. I don't have detail to give, but I know they're really interesting to me. So I'm just pleased that our solar system experts have chosen these targets, and basically everything you've ever heard of in the solar system, we're going to look at it. So on Europa, we want to see can we see the water jets coming out. For Titan, we want to see what's it like where we're going to land the helicopter. So everything we can get in advance of the encounters that we're planning to do would be good to do now. We will certainly be looking for those interstellar comets that might be coming through from other places. We don't have one in mind just yet, but we certainly expect them to come. We're getting better at finding them. So everything from the farthest out to the closest in, which is Mars.
Thank you very much. All right, I believe we have another question from the media.
Thank you. Our next question is from John Amos. Your line's open.
Thanks very much. I think this is a question for Sarah. There's a number that I've been trying to get hold of. And that is the speed at which the fine steering mirror on Webb has to move. Keep the telescope locked on its target, because I think that's controlled by the fine guidance sensor. And then I have a question about gravitational lensing. Hubble used the zoom lens effect a little further back than just its mirror instruments might have suggested it could look. So what does gravitational lensing mean for Webb?
All right, so for the first one, we'll go to Sarah to talk about the fine guidance sensor.
Sure, so I can provide some details for that. So the whole system is really complicated. So first of all, you need to have a camera that looks at the star fields, and then the system determines very precisely where the telescope is actually pointing. And so that becomes part of a feedback loop where that information is fed back into the overall system that points the telescope. There's also a mirror that actually can move to keep the image steady, so you don't necessarily have to move. There's gross motions that the whole telescope does, and then there's very fine motions in order to keep it in position. And the very fine motions are actually maintained by a mirror. So, but it's just a piece of the whole system. But it takes the information from the star fields and then incorporates it in so that all the information can be put together to keep the telescope pointing precisely, so we can get those beautiful images. And I couldn't hear the second question.
Well, the second question had to do with.
No, I was just saying, do you know how fast that fine steering mirror has to move?
Sarah, did you hear the question?
No. I heard the question about the fine steering mirror. No, I don't know that offhand. We can get that information for you, but I don't know it offhand.
And then the second part of the question was about gravitational lensing and how Hubble had used it in the past, and will Webb do something similar? Who'd like to do the gravitational lensing? John?
Yeah.
Okay.
Yeah. I can say a few words. Hubble has discovered, and other telescopes have also discovered, that gravity, as Einstein said it would, will bend light. So that means it's like having an extra lens on the telescope way out there. So we've surveyed the whole sky, and we know where hundreds of them are, and we've chosen a list where we think that'll be the best odds to see something even farther away that's highly magnified by this extra lens in space. So we see these beautiful circles in the pictures where a distant galaxy has been magnified but distorted by an intervening gravitational field. So it's one of our most powerful techniques to see as far back as we can in time. We know where to look, and we know how to look.
Amber, would you like to add something?
Yeah, well, just one of our, one of the early release science programs, some of the very first data that will be taken by JWST in the first year deals with this exactly, is looking for these gravitational lenses in the more distant universe. And one of our scientists at Goddard, Jane Rigby, leads that program.
Absolutely. Sarah, was there something that you wanted to add at the last question?
So one of the Canadian programs that we have is actually going to be using the NEAREST instrument and looking at gravitational lens systems, taking advantage of those cosmic magnifying glasses in order to look at very, very distant galaxies behind big, massive clusters, and then study their properties and just learn much more, what's the shape of them, what are they doing, are they nice and organized, do they have the kind of structures we see in more local galaxies? So those are the kinds of questions. So we have a program also that addresses that issue.
All right. And I believe, does that conclude our questions from the media? Do we have anything else? We have one more news question.
We have a question from Bill Harwood. Your line's open.
Hey, thanks. Hey, John, you mentioned seeing light, the very first light from clouds or big assemblies of the very first stars. Do you guys expect galaxies to exist at that point? I'm just wondering if Webb will be able to solve this chicken or the egg thing in terms of what came first.
I think you're asking about black holes coming before galaxies or vice versa. Now that's
For stars.
The oldest light Webb can see
yes.
obviously comes from stars, but do you expect galaxies to have already assembled by that point, or do you expect that they're still in the process of forming as far back as as Webb can see?
Well, I think we're expecting to see galaxies grow over time. They grow as gravity pulls little bits together. And the movie that we showed you has galaxies pulling together in gravity. So what we see, of course, are the stars. And as was mentioned earlier, they only last for a few million years each. So for us to see a galaxy, it has to be many, many stars so that they're all lighting up at the time that we're looking. So we certainly do expect to see the collective effect of many, many individual stars. But for us, one of the big mysteries is, do those stars make the black holes, or do the black holes help make the stars? So that's the chicken and egg question we're really worried about.
Well, thank you very much. I'm afraid we'll have to wrap up the questions at this time. So that's all the time we have for this briefing, and it's been wonderful to be here with this incredible panel. There's so much more to share about this exciting mission that I really hope you'll join us at 2 o'clock Eastern Time today, because we'll be having another impressive team of engineers and mission planners to walk us through the futuristic technology that enables this golden eye that the James Webb Telescope has to strive, to seek, and to find what's out there. So thank you very much for joining us. I'm Michelle Thaler from Goddard Space Flight Center. Please join us for the 2 o'clock briefing.
Come through. Watch out. Hey, we're moving now. Yay. Here we go. Hang on. To the moon. Whoa. This is wonderful. I love exploring. I've never seen that before. I want the big one. No fair. I saw it first. I'll race you. Ah, you're on. You'll never catch me. Come on, guys. Wait for me. So many places to go. Huh? Yeehaw! On your left. Hey. Here we go. Is everybody ready? Yeah. Season's greetings. From NASA.
A long time ago, all we could do was look up at the stars and wonder what they were. Then we learned, with the help of telescopes and technology, to extend our human senses farther than those first humans could ever imagine. But we haven't reached the end yet. We know there are more wonders out there. We know there is farther yet to see. If we are seeking new views of our universe and discoveries that we can barely imagine today, we need a completely new way to see. Humanity needs to open fresh eyes to see our universe in a way we never have before. Welcome to NASA's Goddard Space Flight Center. I'm Michelle Thaler. In just a few weeks, NASA and its European partner ESA will launch the James Webb Space Telescope, a colossal leap forward in humanity's quest to understand our place in the universe and our part in a story that stretches back to the beginning of time. Today I have the great privilege of hosting a conversation about the inner workings of the Webb Telescope, the largest and most ambitious observatory ever launched into space. While the science goals of Webb promise the beginning of a new understanding of our universe, the technology of Webb is a marvel in itself. And so to get this conversation started, I'm joined by Eric Smith, the program scientist for the Webb Telescope. Good to be here with you, Eric. I'll put my mask on. Yeah. That's right.
Hi, Michelle.
Hi.
It's great to be here.
Absolutely. Tell us a bit about the history of Webb and how it fits in.
Sure. Well, actually, to continue the story about how telescopes and that technology change our view of the universe, I actually want to start in the 1840s, with a telescope that was known by the fantastic name of the Leviathan of Parsonstown. This 6-foot diameter telescope was used to study nebulae, which were clouds in the sky that they didn't really understand what they were comprised of. And what you see on the screen here is a drawing of what we now know is a galaxy. This was made by William Parsons back, I think, in 1845. Now, if we fast forward about 70 years, the world has a new largest telescope. It's the 100-inch on Mount Wilson, and that was used by Edwin Hubble, Hubble the man in this case, and he used this telescope to study these galaxies. By then, we know they're galaxies, and what he found was that the farther away the galaxy was from us, the faster it's moving. He discovers the expansion of the universe with this new telescope that he has. And you can actually trace the arc of a lot of technology and science in astronomy for the 20th century of more or less a chase of galaxies, for seeking an ever farther galaxy, trying to find the very first galaxies. Well, if we move to the end of the 20th century, we deploy the most powerful telescope we've ever had, the Hubble Space Telescope. It too attempts to find these first galaxies. And you'll also see, as the pictures go by here, a comparison of what the Earl of Rosse drew in 1840 to the Hubble's view of M51 galaxy. So Hubble itself tries to find these first galaxies, and it can't. So we know we need to have yet another kind of telescope with even more amazing instruments. That's the James Webb Space Telescope. So not only will it help us complete this chase of galaxies, but it promises to allow us to explore the atmospheres of exoplanets, alien worlds, study how stars form in our own galaxy. And today you'll hear about this amazing telescope and the instruments that will make that all possible.
That's absolutely wonderful. Thank you so much for joining us, Eric.
My pleasure.
So as we talk about the instruments, one of the first things we need to do is talk about this amazing giant mirror. And there's nobody better to speak to us about that than Lee Feinberg. He is the Optical Telescope Manager for Webb here at Goddard Space Flight Center. So Lee, talk to us about the incredible mirror that all these instruments will use.
Well, at 6.5 meters, the primary mirror was too big to fit in a rocket. So we designed it so that it would unfold in space. And it does it like a drop leaf table. But in order to do that, we needed mirrors that could be in segments. And so we've designed the segments to be hexagonal shaped. And that's really nice because all 18 mirrors have the same mechanical design. So we get a lot of economies of scale in how we made the mirrors. And they're actually made out of beryllium. And beryllium is really ideal for these very cold temperatures. So that's why we chose beryllium. And we coat them with gold, a very thin layer of gold. But gold is ideal for the infrared wavelengths, very high reflection, and that lets us see as far as we can and capture all the photons.
It's absolutely wonderful. Is there anything else you'd like to add about the mirror before we go?
No, I mean, the mirror on Webb is actually much larger than previous space telescopes. In fact, it's lighter as well. The primary mirror for the Hubble Space Telescope is 10 times heavier per unit area. So we had to make a much lighter mirror. And this mirror is also, if you compare it against like an infrared telescope, like the Spitzer Space Telescope, which NASA launched many years ago, the Webb telescope is actually 50 times larger. So it has a lot more ability to collect photons, and that makes it much more sensitive. Yet it actually works at shorter wavelengths than the Spitzer Space Telescope, almost down to the wavelengths that Hubble works at.
Absolutely excellent. Well, thank you so much for joining us, and we'll see you for the questions later on.
Okay.
All right. So the next person who will be joining us is Marcia Ricci. And Marcia Ricci is the principal investigator for the NIRCam instrument. So she's actually speaking us today from the University of Arizona. So Marcia, are you joining us?
I'm here and very happy to talk about NIRCam.
Please go ahead.
Okay. Well, NIRCam is a dual-purpose instrument. It is both a science camera and the wavefront sensor. So as Lee mentioned, the telescope mirror comes in 18 segments, and they have to be aligned. And so you can see NIRCam is also dual in the sense of how it was constructed. It has two identical halves bolted together, and that gives us the redundancy so that NIRCam can always be available to align those mirror segments. And this is a big advantage for deep surveys because we can look at twice the sky. And what you're also going to see is a light sensor package, aka detector package, in the test tour here on campus where we gave it its final run through. It has 16 megapixels, with the full instrument having 40 megapixels, which is a lot of pixels for sitting a mile away, a million miles away from Earth. Now, you might ask, what are we going to do with all those pixels? And we have several very big science projects that we're going to do. One of the things that was part of the original plan for the telescope is to look for the very first galaxies to form after the Big Bang. And we know, and here you can see the Big Dipper, and we're going to zoom in to the kind of image that Hubble took as best it can do on these very distant, very red objects. And shortly, a red blob will appear, and that red blob, we're seeing the light from this galaxy as it left only 400 million years after the Big Bang, about 3% the age of the universe. This particular galaxy is extremely bright, and we think it's only the tip of the iceberg of the kinds of galaxies that Webb is going to detect, and we hope we get even closer in time to the Big Bang than what this galaxy is. Now, looking for distant galaxies is not the only science that NIRCam can do. It can be used for many projects, including looking at the atmospheres of planets orbiting other stars, exoplanets. And the way we're going to do that is using the transit technique. And so what we'll do is we will observe a star, a planet will pass in front of it, and the light from the star will be dimmed for a little while. And then if we analyze how that light gets dimmed and look at what colors of light come through, we can analyze the pattern and see what kinds of molecules are in that atmosphere. Now, that's not the only way that we can observe exoplanets. We also have the capability to look at them what we call directly, that is, in the light that they reflect from their parent star. And ordinarily, you can't see these planets. Here's a hypothetical rocket ship going through this exosolar system, and when you're actually there, you can see the planet. But if you move far away, like our vantage point with Webb, that planet gets lost in the glare of the sun, and you have to blot out the starlight using a dark opaque disk that we call a coronagraph. And so that's just a quick sampler of the things that we'll do with NIRCam.
Now, of course, JWST is not just an imaging camera, but it also has a lot to do with spectra as well. So now we're going to Pierre Fruy. He's actually the NIRSpec principal investigator from the European Space Agency, and he'll tell us more about this spectroscopy technique. So Pierre, welcome to our broadcast.
Yes, thanks, Michelle. I'm very happy also to be here, to be able to talk about NIRSpec. So NIRSpec, indeed, its name means near-infrared spectrograph. So it's a spectrograph, and it's part of European contribution to Webb, like the mid-infrared instrument. And NIRSpec is going to allow to probe a wide variety of astronomical objects, from the first galaxies to planets orbiting over stars. And with NIRSpec, it's going to be achieved by analyzing spectra and not images. NIRSpec is a pure spectrograph. So we are all used to images, but spectrograph work a little bit differently. They are going basically to take the light from an object, as you can see on the screen, and split it into its component, creating what we call a spectrum. And spectra contain information about what the object is made, what are its physical, its chemical properties. So it's a treasure trove of information that NIRSpec is going to put in the hands of scientists all around the world. So all JWST instruments have spectroscopic modes. As you have already heard for NIRCam, you will hear for NIRIS, and it's also the case of MIRI. And NIRSpec is going to offer additional choices to Webb scientists. If I take one example, if we take the little red blob that Marcia presented, these very distant galaxies, they are so far away, they are located more than 13 billion light years away, that very little of their light is going to reach us. So to observe them, we are going to have to stare for hours. And this is why NIRSpec is really designed to observe more than 200 of them at the same time, not one. And it's a very efficient use of Webb spatial time. To do that, it's equipped with a very special novel device that you see currently on the screen. These are arrays containing close to 250,000 of very tiny little doors that you can open, close at will. And to observe with NIRSPEC, scientists will pick a patch of the sky, select the objects, open the doors in front of these objects, close the doors for the others, and they will get individual spectra for this object, close to 200 at once. Okay, and that's the first example. And you will see another example for NIRISS of observing multiple objects at the same time. But sometimes scientists actually are not interested in getting 200 spectra of 200 different objects. What they want is to get as many spectra as possible from one object. And NIRSPEC can do that, like MIRI, in fact. And it's going to use what we call a slicer. It's going to slice the image of the object in 30 slices. You're going to see on the screen this image of a galaxy, and you cut it not 30 here, but in NIRSPEC it's 30. Each of these 30 slices is going to give you 30 spectra. So 30 times 30, it means you get 900 spectra at once of a given object. And with that, you're able to map beautifully the physical, kinematical, chemical properties of an extended object, a nice object like a galaxy. So that was basically to give you an overview of what can NIRSPEC do. Of course, NIRSPEC, together with NIRCam, with MIRI, with NIRISS, is going to offer really a very nice toolbox to scientists, a spectroscopic toolbox. And to conclude on this image, which was when NIRSPEC was fully assembled, really now we are in JWST, we are ready, and we are waiting eagerly for launch and to start using NIRSPEC in space.
Thank you very much, Pierre. So in keeping with our theme that this is a very international collaboration, we're now going to Canada. And so for our last guest, we're talking to René Deon, and he is at the University of Montreal. René, please tell us.
Bonjour, Michel. I'm very glad to be here. So I'm going to talk to you about the Canadian. So the Canadian Space Agency is providing two key elements built by ComDev that are now known to be Honeywell. So I'm going to talk about the fine gathering sensor, which is the gather for short. So the gather is not a scientific instrument, but known as a key component of the observatory. So the gather is basically an infrared camera that look at the sky and pick up a star, and we track its movement while we take any observations with all science instruments, because there's inevitably vibrations, and if we don't correct for them, then the images would be blurred. And so what we do, we send a signal to the fine string mirror, a small mirror inside the observatory, that we can tip and tilt 16 times per second, and we can that way get the best possible, sharpest images. And just to give you an idea how accurate the gather is, where the gather will be capable of measuring an angular displacement of the telescope equivalent to the thickness of a human hair as seen from 1 kilometer. Or if you want, it's like being able to see someone blinking from New York City, in New York City from Washington, D.C. So it has to work that accurate to get the best possible images. So on the backside of FGS, we have the scientific module of the Canadian instrument called NIRISS, which is near-infrared imager and slitless spectrograph. So NIRISS is basically an infrared camera operating on the same wavelength range as NIRCam and NIRSPEC, but and can take images like NIRCam, but mostly will be used for spectroscopic observations that Pierre described so well, and also Marcia. So in one mode, we're going to be doing transit spectroscopy that Marcia described very well, but our mode is specialized to look at very bright stars. We can disperse light over a wide wavelength range, but at the same time, making sure that we don't saturate our detector with a very special prism that will allow us to look at planets like the TRAPPIST-1 system. So here's an animation that they illustrate the technique. We're looking after the tiny sliver of light that forms the atmosphere that is filtered by the starlight. This is very difficult to do. We can do that with Hubble. Well, we're going to be able to do it much better with James Webb. So we'll look at a target like TRAPPIST-1. This is the rock star of a planetary system, a system that has 7 planets transiting its star, and 3 of them are right in the habitable zone. So those planets could have life. So the big question is, do these planets have an atmosphere? And we're sure going to be looking for those planets and be able to say whether they have water, CO, and methane in one single spectrum that NIRISS will be able to take. Now, let me move to a second mode, and we move our filter wheel and we put another prism. This time we're going to do slitless spectroscopy. So it's just like near spec, but instead we take spectra of everything in our field of view. Now, this is a picture of our filter wheel, and one of them is has prisms. These are dispersing elements, allowing us to take a spectra. And one special target we want to look at are galaxy clusters. Those are, we're interested in studying the galaxy and the cluster themselves. But we know that these clusters have also hidden mass, dark matter. And that cluster just act like a gigantic cosmic telescope. And we hope to be able to detect very distant galaxy that happens to be behind the cluster, and using the magnification aspect of the cluster to detect those very faint galaxies. Now, slitless spectroscopy is not as efficient as doing slit spectroscopy, but the advantage is that you get everything in the field of view. So in one shot, we'll take spectra of 3,000 galaxies, so about 30 times or 20 times what near spec can do. Less efficiently, of course, but we may find some very very distant galaxies, and then tell near spec, MIRI, go here, put your slit here, and let's take a spectrum of these very high distant objects. And finally, and not least, we have another mode in NIRIS that called aperture masking interferometry, which is basically inserting a mask inside the filter wheel that will block most of the light of the telescope, which is kind of strange, right? But will take the light of only 7 segments. And that way we'll be able to detect very faint companion close to the star, well within the dark spot that Marcia was mentioning. And so we're going to be able to detect new exoplanet, young gas giant planets, or planetary system, young planetary system like the one we've just shown. We're absolutely excited to get NIRIS on the sky, and we can't wait for the launch.
Thank you very much, Rene. So it's been a long journey to get ready for the launch, but it pales in comparison to this great journey ahead. Webb needs to travel 1 million miles away from Earth before it can even begin its quest for ancient light. That rocket road trip begins at an extraordinary facility located in Kourou, French Guiana. The Guiana Space Center is a tropical facility, but it's also a gateway to the stars. Few spaceports on Earth have soundscapes that include the roar of rockets, followed by the sounds of tropical jungle, once rising spires of fire disappear above the clouds. Once Webb's Ariane 5 leaves the launch pad, flight control transfers to the Mission Operations Center in Baltimore at the Space Telescope Science Institute. It's here where mission managers will not only control the spacecraft, but also gather data from the telescope's scientific instruments. So we're going to take a quick break now, and when we come back, we're going to be taking live questions from the media. If you have questions of your own on social media, you can use hashtag NASAWeb. So join us in a few minutes, and we'll be back to actually talk to this extraordinary panel of scientists and engineers about the inner workings of the Webb telescope.
Our universe is a wild and wonderful place. In NASA's Curious Universe podcast, NASA is your tour guide. Join astronauts, scientists, and engineers on a new adventure each episode. Investigate black holes. Spend a day on the International Space Station and meet the experts behind the revolutionary James Webb Space Telescope. Find NASA's Curious Universe in your favorite podcast app or by visiting nasa.gov/podcasts.
What's out there? Let's find out. The James Webb Space Telescope Augmented Reality app. Whoa! Check out the most extraordinary scientific instrument ever designed in your own space today, only from NASA.
Welcome back to the James Webb Space Telescope pre-launch briefing. I'm Michelle Thaler, and we're here at NASA's Goddard Space Flight Center. What we're going to do now is take live questions from the media. And on social media, if you have questions of your own, just join us at hashtag NASAWeb. So at this time, I'm going to ask the operator, do we have the first question for our panelists?
Yes, thank you. At this time, for phone line, it is star followed by number 1. Should you have a question, please unmute your line and record your name clearly as prompted. Again, with phone line questions, it is star followed by number 1. And our first question is from Bill Harwood. Your line's open.
Hey, thank you very much. Bill Harwood, CBS News. For Eric or Lee, maybe, I'm not sure, but can you provide some detail about how you get Webb into focus? I'm interested in how you'll use NIRCam, I guess, to position each mirror segment, how the position actuators work, how that one works that can change the shape of a segment slightly if necessary. and just how that process works out to bring those 18 individual images down to that one diffraction limited image. Thanks.
Yeah, sure. So when we first start, when we get the very first light from Webb, which we'll be using the NIRCam instrument, the primary mirror segments are actually highly misaligned by millimeters. And so they actually act like 18 separate telescopes. They share a secondary mirror, but it's essentially like we'll get 18 images of a star when we look at just one bright star. And so our goal will be to first align those individual telescopes and then put them on top of each other. We'll take those 18 spots, we'll put them right on top of each other, but each of the telescopes are still not what we call phased up. And by phasing, I mean we have to improve the alignments by a factor of 1,000,000, so that the entire primary mirror is aligned as though it's within about a 5,000th of a diameter of a human hair. And we have a series of algorithms. It actually takes several months to do this. We start with algorithms that are easier to do, like moving the mirrors around, but as we get towards the end of these algorithms, we actually borrow a couple of algorithms, one from the Keck telescope, which does the phasing that gets us within a wavelength of light. And then at the very end, when we get the final curvature of the mirror, we're actually using an algorithm that was perfected when we were trying to determine the prescription of the Hubble spherical aberration problem. So we've borrowed from previous telescopes, and we go through the sequence of algorithms, and about 120 days in, we should have an aligned telescope.
Wonderful. Okay, we're now going to go from questions from social media. This is a question about, I believe this was probably going to NIRCam, because the question is, how clear will Webb's pictures of Mars be? And so, Marcia, was that one that you could answer about the clarity of images of planetary objects like Mars?
I can answer that in part. One of the big challenges is that Mars is actually very, very bright in the infrared. And so if we want to take an image, we have to take a series of quick snapshots of just a little portion of the disk and then stitch them together. And a complication is that Mars rotates while we're taking the picture, but some schemes have been worked out, and I think when we get to the outer solar system, planets like Uranus and Neptune will be much easier to do, but they will give us images that will rival what we've seen from the Voyager flybys, but being able to do it in the infrared, we'll be able to trace out some of the molecules in those planets' atmospheres, things like methane. So we'll be able to look at Mars, but it takes a lot of effort because of how bright and how quickly it rotates.
All right, as far as some more questions from social media, I guess this one is actually one that we could have answers both with spectra and with images. The question is there a possibility to look at Oumuamua as it continues its journey away from the sun using the James Webb Space Telescope? Oumuamua was a comet that actually we believe came from another solar system. And there are more of these objects that we're going to find with the Webb. Can anybody answer the question about information on interplanetary comets, intersolar system comets?
I think if we have an adequate orbit, we could point, but I don't know if we know its orbit well enough to be able to point to where it has traveled to now in space, because it spent such a short time in the solar system, it kind of whizzed by. And whether we know exactly where it's going accurately enough to point Webb, I'm not sure.
Thank you. Would anybody like to add anything else, or shall we go move on? Okay. So the next question I believe we have is from the media. The operator?
Thank you. Our next question is from Irene Klotz. Your line's open.
Thanks very much, Irene Klotz with Aviation Week. I had a question about imaging these earliest structures after the Big Bang. Are scientists dependent on gravitational lensing with JWST, or is that something that JWST will be able to see directly?
Eric, would you like to take that?
I can
Marcia
answer.
Sure. Marcia, please go ahead.
Right. We hope to be able to image these very distant galaxies directly without the help of gravitational lensing. And if there are ones even only a hundredth as bright as the one that I showed in the video, we'll be able to do a lot. But the virtue of gravitational lensing is that it magnifies. And so if we think about whatever ones we can see directly with NIRCam, we could go after somewhat fainter ones using gravitational lensing. So we may learn the most by combining just straightforward imaging on a blank piece of sky with something that's been gravitationally lensed.
Eric, did you want to add anything to that?
No, I was going to say exactly what Marcia said. We'll do both things
Absolutely.
with Webb.
All right. So our next question is from the news media. Please go ahead.
Bill Harwood, your line's open.
Oh, thank you very much. I think this is for Marcia, but you know, I realize that spectra are key to Webb's operations, but the public will inevitably compare Webb's pictures with Hubble's, which, you know, everybody's familiar with. How will the images from this infrared telescope compare to what we're used to seeing from Hubble? I realize you've been asked this a million times. I'm just asking it one more. Thanks.
Well, in terms of the level of detail that we can see, we'll be able to see as fine a detail as Hubble, even though we're working at much longer wavelength. But what's going to be dramatically different is using the infrared, we see things very differently. So if you think about the image of the pillars of creation that you get from Hubble, if you take a similar picture with NIRCam, you will see through those pillars, the dust will basically disappear and you'll see stars inside. And if you go a step longer and look with MIRI, that dust that blots out the stars in the Hubble picture will become glowing warm dust and visible as a source of bright emission in MIRI images. So the images will have as much detail, but a very different character.
Thank you. Okay, let's go to another question from social media. So this one is a spectroscopy question. This might go to Pierre. Are there specific elements that we're looking for in the atmospheres of exoplanets? Is the Webb telescope tuned to look at certain elements in a spectra?
Yes, and I think it's actually applicable to Near East, to NIRCam also. One very nice thing about having an infrared vision is that infrared is a place where you get the signature of very interesting molecules. So we are talking about water, carbon monoxide, methane. So these are really molecules we are interested to learn if we are present in these planets which are orbiting over stars. So yes, definitely there's a long list actually of molecules that we will be looking for and trying to understand what is the composition of these atmospheres. And René was talking about planets which are in the habitable zone around their star. So obviously there we are going to look at things like water, because it's very interesting to see what are the conditions there. Ultimately, that's going one step toward understanding if life is possible on other planets. And that's quite a quest, actually.
Yeah, I would just add that we'll have also the capability of detecting water clouds potentially in these temperate planets. So and also that the MIRI instrument will have sensitivity to for the ozone molecule. So that's a very exciting molecule to look for. Admittedly, quite difficult to detect.
As far as questions from the social media, we have sort of a follow-up on that. It says, will JWST observe the Alpha Centauri system, including Proxima Centauri and Proxima b, the exoplanet? Are there plans to observe that?
I'll take that one, Michelle.
I can take that one. There's plan there are proposals to look at this planet, and a bit like Mars, this is a very bright target, and so we know that the Proxima b does not transit its star. And so one way to do it is by measuring either the reflected or the thermal component from the planet using the MIRI instrument. So it will likely be observed with JWST. Yes.
Anything to add, Eric? Okay, sounds good. All right, we have another question from the media coming in. Operator, please.
Thank you. And once again, please press star followed by number 1. Should you have a question, that is star followed by 1. And we have a question from Bill Harwood. Your line's open.
Yeah, hi, this is number 3 for me. I apologize for that. And Just FYI, guys, it took a really long time to get logged into this call, so I'm not sure how many reporters had the patience to stay on the line. But my question's for Lee again. Can you walk us through the light path and tell us a little bit about how an astigmat works, and with some emphasis on the steering mirror, exactly where that is in the path and how you use it to keep Webb so properly positioned? Thanks.
Yeah, so Webb is actually what's called a three-mirror astigmat, and that means that there's actually three mirrors that work together to form really the telescope. This is a little bit different than what a lot of people are used to. For example, in the Hubble Space Telescope, it's a Cassegrain telescope that's a two-mirror system. So we went with the three mirrors to get this very wide field of view. And so you have the primary mirror with the 18 segments. You have the secondary mirror, which is out on that tripod that deploys. And then we have a large elliptical surfaced tertiary mirror that's inside of what we call the aft optic system. And that actually sends the light to what's called the fine steering mirror. The fine steering mirror is actually at a place where you actually get an image of the primary mirror. So it has a little mask around it that looks a little bit like the primary mirror. And it's a flat mirror, but behind it are special actuators that work at the very cold temperatures that all these mirrors work at, the minus 400 degrees Fahrenheit. And they point that fine steering mirror, and they work in tandem with the guider that Renee had talked about. The guider figures out where a star might be slightly drifting to as the telescope slightly drifts its alignment, feeds that to the fine steering mirror, and that fine steering mirror will keep us pointed, and it'll keep that image looking very crisp.
Thank you. And actually, this one as well, I think, is going to go to Lee. We have a question coming in about gold. So can you talk about why the telescopes are coated with gold?
Yeah, I know it does make it look good, but that wasn't the reason we selected gold. It turns out, if you look at the wavelengths of Webb, I mean, it's a very broad wavelength range, especially if you compare it, for example, to Hubble. It goes all the way up to 28 microns. That's the wavelength. But on the short side, it actually goes into the visible. So it's a very long wavelength range. And we wanted a material that would reflect the maximum number of photons. And so if you pick a material that doesn't do a good job at that, it's almost like having a smaller telescope from the point of view of sensitivity. So you really want to use the optimal material. And it turns out gold has an amazing reflectivity over all of these wavelengths. It's almost 98% reflective. So we lose very few photons. And the alternative materials just weren't as good in their reflectivity. So we really went for getting as much throughput as we could.
Absolutely. So going back to our social media questions, there's an instrument we should talk about a little bit more, and that's MIRI, our mid-infrared instrument. So the question is, what are some specific advantages of viewing the universe in mid-infrared as opposed to near-infrared? Would someone like to talk about MIRI a little bit?
Maybe I can say a few words about MIRI, and maybe Marcia will also complement. But usually astronomers, when we look at objects, when we look at different part of the light, be it near-infrared, mid-infrared, we actually see the objects in a different way. We can see different components of the object. And Marcia was talking about the pillars of creation, where in the near-infrared, we just go straight through the dust and see what is hidden behind the dust. But this dust, when you go to the mid-infrared, it becomes suddenly, it is an emitter of light. So you see the dust, so you can study its properties. So there are really very interesting things to use MIRI and to complement, as a complement also to the near-infrared observations. And when we talk about also a lot about these very first galaxies, and the very distant one, they get part of their light which is shifted in the near-infrared, but also part of their light which is shifted in the mid-infrared. So only MIRI on Webb will be able to see that. And this light in the mid-infrared contains additional information. As an example, on the existing population of stars, or slightly older population of stars in these galaxies. So this is really something that you can only see in the mid-infrared. So it's bringing a huge amount of new information and a very interesting new capability to Webb.
Thank you very much. All right, going back to our social media questions, we have one from Jonathan Amos of the BBC. The question is, what will you be able to see in the plumes of Enceladus and Europa? So once again, sort of looking for the signs of life. Would anybody like to talk about what we might be able to see in the plumes of Enceladus and Europa? I know that, Eric, would you like to talk about that?
Well, I'll just say that as a preface to that, Webb looks at things that are proposed by the scientific community, and so each year we conduct a competition and people put in their best ideas of what to look for. And so the question is about Enceladus and the water plumes and what might be in those plumes. And so certainly Webb will take a look at that to see what other chemical constituents there might be in those plumes with, again, a new set of eyes that we don't have, these infrared eyes, both near and mid-infrared. So if we haven't done it in that first year, we'll probably do it in the second year because the scientific community is always coming up with new ideas and they get to propose once every year.
All right, going more to social media questions. So Lee, once again, this is a question about the scheduling. This isn't a telescope that you just open up and it immediately works. You need to focus all of the segments. Can you give us a time frame as to when that will be happening?
Yeah, well, unfortunately, the reason we can't get things done faster is we're limited by physics. And really what that means is the cool down of the telescope and the cool down of the instruments. And cooling to minus 400 degrees Fahrenheit takes a long time. And the instruments as well have to cool their detectors to a cold enough temperature that they're sensitive. So NIRCam will be sensitive a little after 30 days, and the guider a little bit after that. And so we'll be using the guider and the NIRCam instrument to help us with the focusing, but we can't get started until they get cold enough. And then we can't actually align the telescope fully for another about month because we need the telescope itself to get so cold that it starts to get really stable. And so it does take several months, but by about 4 months into the mission, during the commissioning, we should have the telescope fully aligned, and we'll be handing it off to the science instrument calibration team for calibration.
Thank you. All right, I believe we have another question from the media. Operator, please.
Thank you. Our question is from Irene Klotz. Your line's open.
Thanks. I was wondering if the 4 instruments can operate simultaneously, or do they? Is that not possible? And also, is there some technical reason why the near-infrared imager was selected to be the wavefront sensing services over the mid-infrared instrument? Thanks.
Eric, would you like to start? Yes.
Sure, we'll start with the second one first. We've actually designed the telescope to be diffraction limited at 2 microns, which is in the NIRCam's wavelength range. And so that's why you want to use it to do the shaping of your mirror. And then the first part of the question was, again?
Could you repeat the first part of the question?
Yeah, if the 4 instruments can operate simultaneously.
Yes, in fact, they can operate simultaneously. We call this parallel observing, where you can operate more than 1 instrument at a time. And they may even be looking at slightly different pieces of the sky for different scientific reasons. But you can operate them at the same time and bring those data back and get even more science while you're doing one with 1 instrument.
Excellent. Anything to add? All right. Going on to our next question, again from Jonathan Amos on BBC. This one, I think, is going to go to Renee. How fast does the fine steering mirror have to move? How many adjustments a second?
Oh, well, I guess that's a good one for Lee. All I can tell you is that we need to make these measurements 16 times per second. And so, but I can't tell you exactly what the speed is of the steering mirror. Maybe Lee can answer that one.
The loop closes at about 1 hertz. So that's about every second we close that loop, which is a little bit slow. You know, it's not super fast, but it's enough to correct drifts. And that's really what we're trying to do is the spacecraft slowly drifts, for example, thermally relative to the telescope. Those are the kinds of things. So there's slow effects we're trying to correct.
Absolutely. All right. So let's see. I'm seeing if we have any questions coming in on social media. Let's go to a question about using, okay, here's one. How much will Webb be able to determine the rotation rates of exoplanets, including potentially habitable ones, by tracking nature's surface features in optical or infrared? So is there a way that Webb has that will actually be able to determine rotation rates of exoplanets? Anybody want to talk about that one?
I can take that one. It's going to be very difficult to do that for a small rocky planet, but it's been done already with Hubble to detect rotation periods of gas giant planets, and by looking at and measuring winds in these atmospheres. So we think Webb will be even more capable of doing that. But for rocky planets, it's difficult, but we know from physics that in all likelihood these planets that revolves around their star, they're tidally locked. That is, they're always looking the same phase to their star. That is, they're rotating with the same period as their orbital period. Yeah.
Thank you very much. All right, we have a question coming in on social media about constructing the mirror, about where this material came from, the entire path of that.
Yeah, well, this is actually quite an amazing story, and it really was a team effort across the entire United States. It starts actually in Utah. That's where the beryllium was mined. We actually developed a new form of beryllium just for the James Webb Space Telescope. It's an optical grade that's more uniform than has been done before. And the billets of that, the blocks of that, were actually made just outside of Cleveland, Ohio. And then those blocks were sent to Cullman, Alabama. That's where they were machined. And there was a large machine shop that we built specially just for these mirrors. After they were machined, and that means lightweighting them and getting the surface rough, the mirrors were sent to Richmond, California. That's where they were polished. It's actually the same company that polished the corrective optics that fixed Hubble, but this was beryllium and large mirrors. Then the mirrors were actually sent for coating just outside of Philadelphia. And they also made stops in Boulder, Colorado, where they were assembled. Ball Aerospace was the group that designed and assembled them. And ultimately, they made a trip to the Marshall Space Flight Center for testing. We actually had to test them at cold temperatures to determine how they deform and send them back for polishing and then back for measurements. And then finally, they made their way here to Greenbelt Goddard Space Flight Center, where the telescope was assembled.
Absolutely. All right, a question from social media again. How long are reaction wheels, gyroscopes, etc. on Webb designed to allow it to operate compared to how long the reaction wheels allowed Kepler to operate? Also, how many reaction wheels are there? More than 3? So it's about the reaction wheels and the gyroscopes and how long they plan to last.
Sure, I'll take that one. There are 6 on Webb, and they're different than the ones that were put on Kepler. I think the ones that are flying now that are analogous might be on the Chandra X-ray Observatory. So we anticipate them to have a very long life, and those aren't actually the life-limiting feature on Webb. Rather, it's our station-keeping fuel, which we have 10 years worth, at least 10 years worth of fuel.
Thank you very much. All right. So this is all the time that we have for today. Thank you so much to our guests, and thank you for joining us as we count down to the amazing launch of NASA's new James Webb Space Telescope. I'm Dr. Michelle Thaler at Goddard Space Flight Center. Thank you so much for joining us.
And thank you. This does conclude the call. You may disconnect.
It's the first word from space before history is made. From landing a man on the moon to assembling the International Space Station, NASA's Johnson Space Center serves as the iconic beginning to some of the greatest moments in American history. Moments that are triumphs of engineering and international cooperation. Today, we are leveraging our past successes to create even more daring missions from the moon. Made possible with the Orion and Gateway programs, which are both orchestrated out of Johnson, the desolate moon will serve as NASA's jump-off point as we journey to unlock the secrets of the universe and understand how it all began. Today, we push forward to the moon. Tomorrow, we leap to greater heights and new destinations. There is history to be made. In Mission Control, we eagerly anticipate the first transmissions from unexplored worlds. Giant leaps start here.
This is a science mission on par with Apollo missions, Space Shuttle, International Space Station, and Hubble missions. For nearly 2 decades, thousands of people around the world, many spending their entire careers, built the James Webb Space Telescope. And it all comes down to this.
Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1 million miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space.
We want to see distant parts of the universe humans have never seen before. Looking back in time almost 14 billion years to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sunshield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4 meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our ride to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To cheat the fairing size limit, we built Webb to fold, like origami, to fit inside the rocket fairing. And this brings us to our most challenging part of this mission, unfolding it in space.
Thank God.
Think of what you're doing. You're taking this extraordinarily delicate, precise, state-of-the-art scientific instrument, you're slapping it on a rocket, and for the next 8 minutes, the explosion from that rocket is following you into outer space. Vibrating you, shaking you. Everything that goes into outer space has to live through this environment and work once it gets there without having someone come to fix it.
Weeks. That's how long it will take to fully deploy the Webb telescope. We can take longer if we need to, but those 2 weeks after launch are going to be nail-biters. This is the Mission Operations Center at the Space Telescope Science Institute in Baltimore. Those 2 weeks after launch will be like our Super Bowl, World Cup, you pick the analogy. Years of training comes down to these moments.
The Webb Observatory has 50 major deployments, 50 depending on how you categorize them, and 178 release mechanisms must work to deploy those 50 parts. Every single one of them must work. Unfolding Webb is hands down the most complicated spacecraft activity we've ever done. Then again, nothing about Webb is easy. We've never done any of this before. There's nothing simple about sending anything into space. You can't do it without taking risks.
This mission is squarely in new spacecraft territory. Webb is the perfect example of science desire driving engineering capability to new frontiers. Webb's unique design was born from reasoned engineering to accomplish its science goals.
Here's the plan. Shortly after launch, we unfold Webb's solar panel for power and our Huygens antenna for communication. About 12 hours later, we have an important engine firing that sends Webb on the proper course towards its orbital destination, about 1 million miles away. That's where Webb will do its science. Webb will be moving so fast, it passes the moon's orbit in 1.5 days, half the time it took Apollo astronauts to reach lunar orbit. First, we lower the sunshield pallet. Then raise Webb's primary mirror and instruments away from the sunshield. The solar wind will push us around with the sunshield open, so we'll unfold a trim tab to help keep us stable.
We got these huge, iconic, golden segmented mirrors that will help us deliver amazing new images from the cosmos. But in some ways, the sunshield is a lot more complicated, and it's just as essential. Without it, nothing works.
Here we've got 5 sunshield layers of approximately 8,900 square feet, almost the size of 3 tennis courts, of very thin Kapton material, about 1 to 2/1000ths of an inch thick. Making them go where you want them to go in 0G is extremely challenging.
The sunshield shades the telescope from the heat of the sun, earth, and moon. The concept is simple, but there is nothing simple about the design or operation, especially when you get to space. Webb's sunshield assembly includes 140 release mechanisms, approximately 70 hinge assemblies, 8 deployment deployment motors, bearings, springs, gears, about 400 pulleys, and 90 cables totaling 1,312 feet. All this just to keep the sunshield under control as it unfolds. First, we release these special restraints that protect the sunshield during launch. They roll out of the way, but not all the way until we are ready to deploy aside. Next, we release a set of covers over the core region. Now comes the critical point. All 107 sunshield release mechanisms need to fire on cue. 107. They free the 5 sunshield layers, allowing them to extend as the mid-booms deploy.
Sunshield fully deployed, we start setting up the optics. First, the secondary mirror is extended and locked into place, and a special radiator behind Webb is extended, which helps further lower the temperature of the science instruments. Finally, we open the primary mirror's wings and lock them in place. With that done, Webb is in its final configuration, but we're not done yet.
After 47 deployments, and accomplishing the hardest spacecraft unfolding NASA has ever done, Webb still won't be ready for science.
While the instruments cool, we'll control motors behind each of Webb's 18 mirror segments, the secondary mirror, and the fine steering mirror located inside the center of the primary mirror. We'll precisely align the mirror segments to form a perfect mirror. Then, Webb will be ready to explore the cosmos.
Come through. Watch out. Hey, we're moving now. Yay. Here we go. Hang on. To the moon. All right. Whoa. This is wonderful. I love exploring. I've never seen that before.
I want the big one.
No fair! I saw it first!
I'll race you.
Ah, you're on.
You'll never touch me.
Come on, guys. Wait for me.
So many places to go.
Huh?
On your left.
Hey. Here we go. Is everybody ready?
Yeah.
Season's greetings.
From NASA.
Good morning and Merry Christmas from the Guyana Space Center in Kourou, French Guiana. You are looking live at the European Ariane 5 rocket on the launch pad here in Kourou, where fueling of the vehicle is moments away for the launch of the James Webb Space Telescope at 12:20 Greenwich Mean Time, 9:20 a.m. here in Kourou, 7:20 a.m. Eastern Time. Within the last hour, mission controllers here at the Jupiter Control Center, launch engineers at the nearby Launch Control Center, and Webb Telescope Observatory engineers at the Space Telescope Science Institute in Baltimore received a comprehensive weather briefing and were told conditions were go for the start of the loading of 175 tons of propellant into the core or first stage of the Ariane 5 rocket. 150 tons of liquid oxygen and 25 tons of liquid hydrogen will soon be flowing into the first stage tanks of the Ariane 5. This process will take about 2 hours to complete. About an hour from now, some 15 tons of propellant will be loaded into the second stage or upper stage of the Ariane 5, another 2-hour process, which should be complete around 1 hour and 22 minutes before launch. A series of weather briefings will be conducted over the next few hours to ensure that conditions remain favorable for launch. All this while Webb systems are being carefully monitored for the momentous launch of the largest, most powerful telescope ever sent away from our planet. So as the James Webb Space Telescope sits passively atop its Ariane 5 rocket, poised to begin its long-awaited mission, the fueling of the Ariane 5 soon to begin. Everything is in great shape, a green board here in the Mission Control Center. We'll be back with you soon at 6 a.m. Eastern Time with our comprehensive launch coverage, the broadcast, a collaborative effort between NASA and the European Space Agency. A reminder, launch is scheduled at 7:20 a.m. Eastern Time. This is Ariane 5 Mission Control in Kourou.
7, 6, 5, 4, 3, 2, 1, top. Allumage Vulcain. Allumage EAP, décollage. Allumage EAP, décollage. 7, 6, 5, 4, 3, 2, 1, top. Allumage Vulcain. Allumage EAP, décollage.